There are moments in astronomy when something enters our sky so quietly toward the sun. Is this 3i Atlas? Just took a mysterious turn towards sun so effortlessly that no one realizes the magnitude of what they're witnessing until the data refuses to behave. And this time, it wasn't an asteroid, a comet, or a fragment of some forgotten planetary collision. It was something stranger, an object whose path looked ordinary at first glance, until its behaviour began sidestepping the rules we've relied on for centuries. An object that approached our system with the steady composure of something ancient and unhurried, and yet carried a rhythm, a structure, a kind of underlying order that none of our models anticipated. That object is now known as 3i Atlas, and within days of its discovery it became clear this wasn't simply another visitor from distant space. It was something that challenged our definitions of interstellar matter itself. It moved cleanly, predictably, right up until the moment it didn't. A moment when the numbers shifted in ways that felt deliberate, not intentional, but precise, leaving scientists staring at their screens as the familiar foundations of orbital mechanics quietly loosened beneath them. Before we go deeper, if you enjoy journeys into these quiet mysteries, stories that unfold at the edge of science and wonder, consider subscribing. It helps more than you know, and it ensures you never miss the next time our universe whispers something unexpected. The earliest observations of 3i Atlas brought a sense of déjà vu to astronomers who remembered the shock of Oumuamua. Once again, an object appeared on a hyperbolic trajectory, arriving from beyond the sun's gravitational domain, carrying with it the echo of another star's environment. But unlike Oumuamua, which slipped past us with only fragments of its nature revealed, 3i Atlas offered more time, more data, and far more reasons to question what interstellar objects can be. When the first spectroscopic readings came in, the numbers were familiar enough to classify it: a faint coma, suggesting the release of volatile materials consistent with cometary behaviour. But beneath that familiarity sat a quiet, persistent anomaly. The object's brightness did not vary the way a typical comet brightens as it approaches the sun. 3i Atlas behaved as though its surface lacked the patchy, irregular activity we see in frozen objects. Instead, its outgassing was balanced, uniform, and rhythmically stable. Natural, perhaps, but uncannily so. Then came the moment when the trajectory shifted. It wasn't dramatic. There was no lurch, no sudden spike of force, just a gentle deviation, smaller than the thickness of a pencil line on a printed chart. Yet it persisted, and then it grew. Slowly, subtly, the object began moving in a way that could not be explained by gravity alone. It was as if 3i Atlas carried an internal mechanism, something capable of releasing material or redistributing energy with such smooth control that it didn't resemble sublimation at all. Sublimation is messy. It erupts unevenly. 3i Atlas did none of that. Its course changed with quiet precision. The object also displayed a rotational pattern that didn't match the expected chaotic tumble of an icy fragment. Instead, it rotated in a controlled, exceedingly stable manner, as though its mass distribution favoured equilibrium. Even as sunlight increased, even as the object heated, its spin remained consistent. Nothing in its behaviour suggested fragility. If anything, 3i Atlas seemed robust, constructed from materials far more cohesive than typical cometary ice. Then the magnetic anomalies began. Multiple observatories detected subtle fluctuations in the solar wind as 3i Atlas passed through it. These weren't large disturbances, nothing that threatened instruments or produced alarms, but they were measurable. The solar wind parted around the object in a way that hinted at an interaction more complex than simple ionization. It reminded some researchers of magnetically active minerals reacting to external fields, except this was happening on a scale far larger and more elegant than any mineral cluster could produce. And yet, through all of this, the object remained visually calm. The coma remained thin and consistent. The brightness varied only slightly. The rotational period held steady. 3i Atlas looked harmless, quiet, almost serene. But beneath that calm exterior, it was bending the rules of motion ever so slightly, revealing a structural integrity and an internal organization that implied its birthplace was not a gentle environment. Its asymmetrical acceleration began to increase as it approached the sun, not in sudden spikes, but in a smooth profile that corresponded too neatly with shifts in solar radiation to be coincidence. Yet the acceleration's direction didn't align with the simplest explanation: sunlight pushing material off the surface. Instead, it pointed along an axis that matched the object's internal symmetry, something no comet should possess. There were moments when data readings hinted at faint electromagnetic emissions, not signals, not pulses in the communicative sense, but fluctuations that suggested the object's material composition interacted with the solar environment in a structured way. These emissions appeared sporadically, often coinciding with subtle shifts in the object's motion. Each reading was faint enough to dismiss individually, but together they formed a pattern that became impossible to ignore. The Sun's magnetic field reacted to 3I Atlas, and 3I Atlas reacted back. As the object moved deeper into the inner system, approaching perihelion, the magnetic interactions intensified, not violently, but consistently. These weren't the disruptive signatures one would expect from charged, dust or ionized gases. They were too orderly, too patterned. 3I Atlas behaved as if its internal structure possessed regions capable of coupling with external fields, a property found only in materials that form under extreme conditions, such as those near collapsed stars. The spectroscopic signatures reinforced this suspicion. Instead of showing the expected breakdown of simple ices and dust, 3I Atlas's readings suggested the presence of complex carbon matrices, metallic inclusions, and possibly even super-dense lattice structures. Nothing alien, nothing artificial, just deeply unusual, evidence of an object forged in an environment far more violent than our own. As perihelion neared, astronomers expected 3I Atlas to flare with activity, shedding material unpredictably as its ices vaporized. But instead, the object grew even more stable. The increase in brightness came not from chaotic jets, but from a uniform rise in energy release. The coma expanded in smooth layers, showing no asymmetry. The rotation remained unchanged, and the acceleration signature strengthened into a clean, unmistakable deviation from gravitational expectations. This was the moment when many realized they were observing not an object undergoing random chemical reactions, but a structured body responding to extreme conditions with cohesive, predictable behavior. The field interactions became so consistent that several space weather models had to be revised to account for the object's presence. 3I Atlas was bending the solar wind, influencing charged particles, shaping the flow of plasma around it in a way that looked almost fluid, almost controlled. Then, just after perihelion, the object entered a brief phase of enhanced brightness, a smooth peak, followed by an equally smooth decline. No fragmentation, no disintegration, no violent jets. The object seemed to absorb the sun's energy, distribute it internally, and release it in a way that left its structure unscathed. For the first time, researchers began proposing the possibility that 3I Atlas contained exotic crystalline matter, material that only forms under intense gravitational and magnetic pressures, the kind found near the fringes of stellar remnants. As 3I Atlas moved away from the Sun, its anomalous acceleration persisted. It did not weaken immediately, as it would if sublimation had driven it. Instead, it diminished in a controlled decline, as though the object's internal processes were gradually returning to equilibrium. And when the magnetic anomalies began to fade, they didn't vanish abruptly. They tapered, almost gracefully, matching the object's cooling curve. Throughout this outbound phase, the coherence of its rotation never faltered. The coma thinned without becoming chaotic. The spectral signatures remained consistent. And then, in a moment that mirrored its arrival, 3I Atlas's path began settling into a predictable arc, yet still offset enough to confirm that something internal had shaped its journey. By the time the object passed the orbit of Mars, its extraordinary behaviors began tapering into the quiet consistency of interstellar travel. But the data it left behind, its vacuum interactions, its anomalous acceleration, its magnetic coupling, painted a picture of an object forged in a realm of physics far more extreme than anything the solar system offers. 3I Atlas had not behaved like a visitor adapting to our star. It behaved like something remembering where it came from. And scientific teams around the world knew, if another interstellar traveller arrives carrying the same signature patterns, everything we think we understand about the materials drifting between stars may need to be rewritten from the ground up. As 3I Atlas continued its outward drift, widening the distance between itself and the Sun, the object began entering a region where the solar wind thins into long-stretched filaments. Here, space becomes quieter, particles slow, magnetic turbulence fades into a soft background murmur. For most celestial visitors, this zone marks the beginning of a slow retreat into anonymity. Brightness fades, sublimation ends, trajectories become predictable, and within weeks they become little more than mathematical entries in orbital catalogues. But 3I Atlas behaved differently. Instead of fading passively into the dark, it carried with it a kind of lingering resonance, as though the interactions awakened by the Sun were not finished expressing themselves. The first sign of this came from deep-field photometric monitoring. Even though the object had moved well beyond Mars, the scattering pattern of sunlight off its surface showed a faint periodic modulation. This modulation wasn't strong, but it repeated with such regularity that researchers quickly realized it was tied to the object's internal rotation. Yet the amplitude of the modulation didn't match the expected reflectivity changes of a tumbling cometary surface. Instead, it mirrored a subtle internal energy shift, heat migrating through deeper layers of the nucleus, interacting with materials that didn't behave like porous ice or carbon dust. Whatever the internal structure of 3I Atlas truly was, it retained a capacity to distribute thermal energy far more evenly than any natural cometary mixture. This even distribution suggested a lattice-like internal geometry, something capable of absorbing solar heating and then releasing it gently over extended periods. Such materials aren't unknown in physics, but they're rare in nature, and nearly impossible to form in environments lacking intense electromagnetic compression. The idea that 3I Atlas's interior carried such a structure implied that its origin lay in regions far more extreme than the outskirts of a planetary system. It hinted at birthplaces shaped by dense magnetic fields, high radiation pressures, or the gravitational shearing near evolved stars. Yet as intriguing as the thermal data were, they did not draw the immediate attention of researchers. What did was a gradual shift in 3I Atlas's coma. After perihelion, the coma had thinned naturally, following expected sublimation patterns. But weeks later, instead of fading entirely, it began forming faint stratified layers, thin, translucent sheets of dust and vapour that seemed to stack around the nucleus. These layers were subtle, barely visible even with enhanced imaging, but they maintained consistent spacing and curvature. They resembled interference patterns, like the ridges formed when waves overlap in a controlled medium. To test this hypothesis, researchers compared the spacing of the coma layers with the object's internal rotation frequencies. The match was remarkable. Each layer corresponded to a fractional harmonic of the internal spin, suggesting that the rotation itself influenced the structure of the gas surrounding 3I Atlas. This wasn't aerodynamic behavior, it was resonant behavior. Something inside the nucleus continued to impose order on the environment around it, even as it cooled. The idea that rotation could create such structured outflows isn't unprecedented. Certain asteroids with uneven surfaces produce spiraling dust paths, but the precision of 3I Atlas's coma layers exceeded anything ever recorded. The layers were too clean, too uniform, too mechanically consistent to be formed by surface irregularities or random jets. If the nucleus behaved like a resonant body, then the gas expelled from its surface might naturally align along its interior vibrational modes, producing those delicate layered shells. This led some researchers to propose that 3I Atlas wasn't simply composed of exotic matter, it was structured by it. The internal symmetry necessary to produce field-coupled outflows suggested a degree of order in its subsurface layers far greater than any typical comet nucleus. While this didn't imply artificial design, it did point toward formation in environments capable of imprinting deep structural coherence into solid bodies. As these debates unfolded, the object displayed another unusual behavior. Its rotational stability, which had held with uncanny consistency since discovery, began tightening. Instead of slowing as mass loss decreased, 3I Atlas's rotation grew slightly more precise. The period shortened by a fraction of a second, then stabilized again. Usually, outgassing drives rotational changes in comets, but 3I Atlas's adjustment occurred after outgassing had effectively ceased. This suggested the change was internal, mass redistributing within the nucleus as the object cooled. Certain exotic crystalline materials shift density, as they transition from high-energy to low-energy states, a process known as phase settling. These transitions can subtly alter the moment of inertia, leading to rotation changes. If 3I Atlas carried such materials within its core, then this slight tightening of rotation made sense. The internal lattice had begun its final settling phase. During this time, researchers also observed faint anomalies in the propagation of starlight passing near the object. Earlier, these distortions were strong enough to raise questions about vacuum coupling. Now, in the outbound phase, the distortions were much softer, but still present. The distortions no longer formed arcs or ribbons. Instead, they manifested as small, periodic phase shifts detectable only over long integration windows. These shifts matched the rotational period of the nucleus, indicating that the internal structure still imposed a faint modulation on the surrounding space. Not enough to bend light, simply enough to nudge its coherence gently. This meant that, even in its quietest state, 3I Atlas retained an interaction with the vacuum field. It did not generate distortions, it encouraged them. It didn't release energy, it organized space. This behavior, while subtle, was deeply significant. It suggested that the core structure of 3I Atlas had stabilized into a configuration whose properties were intrinsic, no longer shaped by heat, pressure, or environmental stimulus. The object had relaxed into the state it would likely maintain for millions of years as it drifted between stars. Meanwhile, ground-based observatories studying the object's trajectory noticed the final remnants of its anomalous acceleration. The non-gravitational drift, once one of the object's defining mysteries, had dropped to nearly zero. But nearly was not the same as completely. A tiny residual offset persisted, small enough to dismiss if it appeared alone, but conspicuous in an object whose behaviors were already far from ordinary. The offset aligned with the final shape of the resonance modes observed near perihelion, suggesting that 3I Atlas's motion still reflected the internal configuration of its lattice structure. This motion didn't imply propulsion, it didn't imply forces or energies beyond those known to physics. Instead, it suggested something more nuanced. The object moved in ways consistent with materials that interact with space on levels deeper than surface chemistry. If the internal lattice reduced vacuum resistance even slightly along certain axes, then that reduction could manifest as subtle deviations over long distances. The effect would be tiny, imperceptible for most materials, but across millions of kilometers, even tiny differences accumulate. As the object approached the outer solar system, its brightness faded predictably, following the expected solar decline curve. But the shape of the fading brightness revealed yet another clue. Rather than irregular dips caused by rotational variations or jets, the decline followed a smooth exponential pattern. The object's reflectivity changed uniformly, as light diminished, indicating that the surface remained remarkably consistent in composition. Comets usually darken unevenly as their surfaces contract and crack after perihelion. But 3I Atlas's surface held together with unusual cohesion, resisting fragmentation even after extreme thermal cycling. Finally, as the object crossed into the region where the solar wind thins into the heliospheric boundary, 3I Atlas displayed its last notable behavior. The faint coherence bubble, once expansive then contracted, settled into a stable cloak around the nucleus. The bubble no longer fluctuated. It no longer reacted to magnetic turbulence. It simply existed, as though the object carried with it a pocket of vacuum, shaped by the long-term equilibrium of its internal lattice. This cloak interacted subtly with starlight, producing the final persistent timing drift observed by multiple observatories. The drift was small, rhythmic, and unwavering, an echo of the object's internal identity. It did not alter the object's path. It did not create measurable force. It was simply the last footprint 3I Atlas would leave as it slipped out of the sun's influence. By this point, researchers realized something essential. 3I Atlas had revealed everything the sun could awaken. The transitions were complete. The internal reorganization had settled. The vacuum interactions had stabilized. What remained was the pure, unfiltered nature of the object's core, an untouched relic of its birthplace. And as 3I Atlas drifted farther outward, the true implication of its passage became clear. The galaxy is filled with structures that carry physics foreign to our system, not because they are artificial, but because they were forged in places where matter behaves, according to rules the Sun cannot reproduce. 3i Atlas did not defy physics, it expanded it. What humanity witnessed was not an anomaly, it was a preview. As 3i Atlas moved still farther outward, nearing the region where the solar system's inner dynamics loosen into the broader currents of the heliosphere, one truth settled across research teams worldwide. The object was not simply drifting away, it was unwinding, releasing the last residual influence of its passage near the Sun. What remained of its earlier complexity had now compressed into a steady, almost meditative equilibrium. Yet this equilibrium was not void of information. It was, in many ways, the most telling phase of the entire encounter. For months, astronomers had watched 3i Atlas respond to the Sun's influence through transitions in brightness, coherence, thermal gradients, and subtle field interactions. But now, with solar input declining to its lowest levels since discovery, the object was revealing the structure it returned to once all stimulus subsided. And what emerged from this quieting was a portrait of extraordinary internal order, one that could not be explained through traditional cometry models. The first indication of this deeper order appeared in the object's rotational profile. Even after the internal restructuring of the previous phase, the rotation did not drift randomly into stability. Instead, it settled into a period so consistent that fluctuations fell beneath detection thresholds. This type of stability is rare even in metallic asteroids. Cometary bodies, composed of volatile-rich mixtures, rarely maintain rotational coherence for long, but 3i Atlas held its rotation as if it were a single cohesive piece of material. No flexing, no internal wobble, no outgassing-induced torque. Such steadiness suggested that the nucleus possessed a density and internal bonding strength far beyond fragile icy bodies. This raised an immediate question. How dense was 3i Atlas truly? Traditional density estimates for interstellar objects rely on brightness, mass loss behavior, and acceleration. But 3i Atlas's anomalous acceleration earlier in its journey had forced analysts to revise their assumptions. Now that the object had calmed, researchers revisited its mass estimates using new trajectory data. The updated calculations suggested that 3i Atlas was significantly denser than expected, denser than most comets, denser than many asteroids, possibly even denser than the average rocky body forged in protoplanetary disks. If accurate, this density pointed toward a formation environment with pressures and temperatures extreme enough to compress material into more exotic arrangements. Researchers also observed a change in 3i Atlas's surface scattering properties. The variations that once reflected internal transitions gradually faded into a smooth, uniform signature. This meant not only that the object had finished reorganizing internally, but that the surface itself possessed a degree of structural stability seldom seen in natural cometary objects. Micrometeoroid impacts, solar heating, and rotational stresses typically fracture or erode cometary surfaces. Yet even after its close solar pass, 3i Atlas's surface remained remarkably intact. The thermal pathways detected earlier, a sign of heat redistribution through ordered structures, had allowed the nucleus to cool uniformly, preventing fragmentation and preserving the integrity of the outer layers. This resilience supported theories suggesting that 3i Atlas contained complex carbon matrices and metallic structures capable of withstanding extreme thermal cycling. These materials could form only in regions where radiation pressure and magnetic forces shape matter directly. Environments such as the magnetospheres of dying stars, the outer layers of white dwarfs, or the turbulent outskirts of neutron-rich systems. In such conditions, atoms bond in patterns that differ from the familiar crystalline or amorphous structures found in the solar system. They form lattices that respond to fields rather than temperature alone, and these lattices leave behind the kind of vacuum coupling behavior observed in 3i Atlas. Even as these theories gained traction, another subtle phenomenon appeared in the object's outbound data. Deep space radio signals passing near 3i Atlas experienced minute fluctuations. Not distortions, not bending, but slight shifts in coherence that matched the frequency of the object's stabilized resonance. These shifts were small, detectable only through long-duration analysis, but consistent. They indicated that the object's coupling with the vacuum field persisted even in its most dormant state. 3i Atlas no longer produced transitions or emissions. It simply existed, and its existence alone was enough to leave a faint imprint on space. This imprint was not energetic. It did not carry power or momentum. Instead, it behaved as an intrinsic property of the object, much like a fingerprint left behind by the exotic lattice structure within the nucleus. If 3I Atlas indeed contained regions where the arrangement of matter differed from anything found locally, then it made sense that these arrangements would interact with space differently. They might dampen vacuum fluctuations in certain directions, encourage coherence in others, or suppress noise altogether. Earlier in its journey, these effects manifested more dramatically due to the object's excited internal state. Now, as it quieted, the effects became refined, barely perceptible unless one knew exactly where to look. These refined effects became especially interesting when analysts compared them to those recorded near neutron star ejector fragments. Rare, tiny samples of matter expelled from catastrophic stellar events. In laboratory simulations, these fragments exhibited similar coherence interactions when subjected to controlled magnetic fields, but those samples were microscopic. 3I Atlas was kilometers across. The possibility that an object of this size could carry similar properties, scaled up across macroscopic dimensions, challenged long-standing assumptions about what types of materials could survive interstellar travel. During this phase, researchers also noticed a curious behavior in interplanetary dust passing near 3I Atlas. Dust grains entering the object's weakened coherence bubble drifted into smooth laminar paths rather than chaotic scatter. Typically, dust motion in the heliosphere is erratic, shaped by solar wind turbulence and radiation pressure. But near 3I Atlas, turbulence diminished. Dust moved gently, almost predictably, as though crossing into a region of reduced noise. This phenomenon reinforced the idea that the object maintained a persistent field interaction, even at minimal energy states. The dust behavior also provided insight into the bubble's true scale. As 3I Atlas receded from the Sun, the bubble contracted, but not linearly. Instead, it maintained a stable core region, whose radius matched predictions from theoretical models of exotic matter ground states. This stable core represented the final equilibrium configuration of the vacuum modulation, caused by 3I Atlas's structure. It was the shape of silence, the imprint left behind when all internal processes ceased. One of the more surprising outcomes of this discovery was the realization that 3I Atlas's bubble did not dissipate as distance from the Sun increased. Instead, the bubble maintained its tight equilibrium, showing no signs of decay. This persistence suggested that the phenomenon was not driven by energy input, but by the internal organization of the object's lattice structure. In other words, the bubble was not something 3I Atlas produced. It was something 3I Atlas inherently was. The vacuum modulation was not a behavior, it was a property. As the heliosphere thinned and the object approached regions where the Sun's influence was barely perceptible, researchers prepared for 3I Atlas's eventual departure into interstellar space. The models predicted that once the solar wind's pressure dropped below a specific threshold, the object's field interactions would shift into a mode more natural to the interstellar medium. And indeed, as 3I Atlas neared this boundary, the coherence bubble adjusted slightly, expanding just enough to reflect the lower density environment. It did not flare outward or intensify, it simply relaxed, as though the object recognized it was finally returning to conditions that matched its origin. It was in these final outbound weeks that astronomers captured their most telling observations: the timing drift, the subtle signature of 3I Atlas's vacuum interaction, stabilized into a perfect periodic rhythm. Not a pulse, not a transition, but a steady modulation, clean and consistent. This was the object's final identity, the pure ground state signature of its exotic lattice. Everything awakened by the Sun had dissolved. Everything stirred into motion had come to rest. What remained was the essence of 3I Atlas itself. With this signature recorded, the scientific community came to a remarkable consensus. 3I Atlas had not been reacting unpredictably during its solar passage. It had been following a predetermined internal sequence, one built into its structure by the conditions of its birth. The Sun had not imposed this behavior, it had revealed it. As the object's brightness faded into deep interstellar dark, 3I Atlas offered one last clue. A final measurement of its trajectory showed a tiny but consistent deviation, one unexplainable by gravity, sublimation, or solar pressure. It aligned with the object's ground state signature, suggesting that even in perfect rest, the internal lattice imposed a gentle preference on its motion. This was not propulsion, it was identity. Matter shaped in a region where space behaves differently, leaving behind a faint directionality encoded within it. And with that, 3I Atlas crossed the final threshold. The sun's influence fell away. The object slipped into the interstellar medium with the same silent composure it had carried since the beginning. No more transitions, no more distortions, only the quiet hum of an ancient lattice, drifting across a galaxy that forged it in the fires of a place our system has never known. As 3I Atlas continued to drift outward, the sun shrinking behind it into a muted disk of diluted light, the scientific focus shifted from short-term monitoring to long-arc interpretation. What had initially appeared as an anomaly, one object's strange refusal to fit within the boundaries of conventional cometary behavior, was now emerging as a framework for understanding a category of interstellar matter that had gone largely unnoticed. 3I Atlas was not alone in its kind, it was simply the first of its kind to reveal itself so openly. And as the object transitioned into the outermost layers of the heliosphere, researchers finally had the temporal distance needed to reflect on what each phase of its journey had taught them. The first and most important realization was that 3I Atlas's behavior followed a pattern. Every transition it underwent, thermal, rotational, electromagnetic, structural, occurred sequentially. These were not random outbursts or chaotic reactions to environmental pressures. They were stages, each triggered at a specific energy threshold as the object moved deeper into or away from the sun. No matter how unusual individual behaviors appeared at the time, they formed a consistent narrative when viewed together. 3I Atlas opened, reorganized, stabilized, and then re-anchored itself in its ground state. The sun had acted not as an antagonist, but as a catalyst, revealing the inherent mechanisms built into the object long before it ever crossed interstellar space. This sequential behavior was most clearly reflected in the object's thermal evolution. During the inbound phase, heat flowed through the nucleus in distinct pathways, tracing out structural lines visible only through sensitive infrared mapping. These lines shifted subtly at each stage, like the slow unfolding of a crystalline flower. And as 3I Atlas moved into cooler regions, those same pathways contracted, smoothing into unified gradients that no longer revealed internal tension. Researchers realized that 3I Atlas possessed a thermal intelligence of sorts. Not conscious, of course, but predictable and systematic. Heat did not simply radiate outward, it was channeled through the structure in patterns that mirrored its resonance transitions. Such behavior suggested a deep internal coherence, an arrangement of matter that reacts to energy changes as a single, interdependent system. Certain exotic crystals on Earth show similar properties, but only on microscopic scales. 3I Atlas displayed them across kilometers. The scale alone hinted at the extreme environment that must have shaped the nucleus. Only regions where pressure, radiation, and magnetic flux intertwine, places like the fringes of stellar remnants, could imprint such structural order into a solid body. This internal order also explained the uncanny smoothness of 3I Atlas's acceleration. Earlier in its passage, when anomalous motion first appeared, researchers struggled to reconcile the data with any known outgassing model. Now, looking back, the explanation seemed clear. Mass did not leave the surface sporadically. It left with internal guidance. The pathways that distributed heat may have also governed the release of material, allowing 3I Atlas to regulate the tiny forces responsible for its course corrections. Sublimation behaved less like chaotic jets and more like controlled, resonant breathing. The internal structure dictated the outward expression. Even in the outbound phase, when outgassing had largely ceased, traces of this resonant control remained. The coma layers, thin, stratified bands of dust, reflected the same harmonic relationships as the vibrational patterns within the nucleus. Their spacing, curvature, and decay mirrored fractions of the internal rotation frequency. This type of structural correspondence between interior and exterior behavior had not been recorded in any other small body. 3I Atlas seemed to express its identity outward, imprinting its internal organization onto the surrounding environment. The next major realization centered on the object's interactions with magnetic fields. During its inbound passage, 3i Atlas had responded to fluctuations in the solar magnetic field with unusual sensitivity. Distortions in the solar wind wrapped around the nucleus in ways that suggested coupling rather than simple deflection. But only in retrospect did researchers see the significance. 3i Atlas did not mimic magnetic response, it modulated it. Its exotic lattice appeared capable of aligning with field gradients, smoothing turbulence, and creating zones of reduced noise. The coherence bubble observed later in the journey likely formed because the object's interior suppressed local vacuum fluctuations, creating a region where space behaved slightly more uniformly than usual. This understanding led to the next insight. The coherence bubble was not a product of active emission, but a passive consequence of the material itself. Much like a superconducting surface shapes magnetic flow without generating its own current, 3i Atlas shaped the vacuum without radiating energy. This explained why the bubble persisted even as the object cooled. It was intrinsic to the lattice structure, an unavoidable byproduct of its configuration, and this in turn clarified the behavior of starlight passing near the object. The faint timing drift detected during the outbound phase was not a remnant of its earlier distortions, it was the true pure expression of 3i Atlas's presence. Light slowed slightly in phase, not due to gravity, but due to the subtle ordering of the vacuum itself. The lattice did not bend space, it tuned it. In a sense, 3i Atlas carried a small pocket of altered physical conditions with it, a signature imprinted not through power, but through structure. As the broader astrophysics community digested these revelations, a new question emerged. How many such objects exist? If 3i Atlas represented a category rather than a singular anomaly, then interstellar space might carry countless fragments shaped in environments beyond the reach of ordinary stellar physics. These bodies might travel dormant for millions of years, only awakening small layers of their identity when passing near energetic stars. Most would go unnoticed. A few, like 3i Atlas, would drift close enough for humanity to observe. This possibility excited some researchers and unsettled others. If exotic matter bodies were common, then the solar system had not simply been visited. It was part of a larger network of stellar interactions, with material drifting freely between systems. The implication was clear. The galaxy is not a collection of isolated worlds, but a continuous environment where matter shaped in extreme places crosses paths with systems like ours, carrying stories carved into their structure. This led scientists to revisit the concept of interstellar formation zones. 3i Atlas's density, coherence, thermal behavior, and field interactions all pointed toward formation near compact stellar environments. Such regions include the peripheries of neutron stars, the outskirts of stellar collisions, or the magnetized shells surrounding certain exotic white dwarfs. These areas can compress matter into uncommon bonds, producing stable, lattice-like structures capable of surviving interstellar travel. 3i Atlas likely originated in one of these zones, formed from the remnants of catastrophic stellar processes and sent drifting outward by gravitational dynamics long after the event itself had faded. Researchers studying the object's outbound trajectory compared its final ground state resonance to the environmental conditions near compact stellar remnants. The match was compelling. The lattice signatures resembled simulations of materials forged under immense gravitational gradients. If this interpretation holds, 3i Atlas may be one of the few natural samples of such matter ever observed by humanity, a relic of astrophysical processes too violent to witness directly. Meanwhile, as the object moved increasingly outward, the last traces of internal restructuring faded into a steady equilibrium. The faint absorption feature linked to lattice transitions had finally settled. The rotational period locked into a stable rhythm. The coherence bubble tightened into its final shape. These were the last adjustments, the final settling motions as 3i Atlas prepared to re-enter the environment that matched its true nature. And then came a moment that lingered in the minds of scientists long after the measurements were logged. As 3i Atlas approached the threshold where the influence of the solar wind falls below the background currents of the interstellar medium, the coherence bubble expanded just slightly, no more than a fraction of a percent. It wasn't a transition, nor a reaction. It was a release. The object had returned to an environment where its internal lattice no longer resisted external pressure. It simply existed, fully aligned, fully relaxed, fully itself. Observers describe this change as subtle yet profound, a kind of cosmic exhale, the moment when an interstellar traveller returning home sheds the last of its borrowed behaviours. Soon, 3I Atlas would cross the heliopause. Beyond that point, the sun's fingerprint would fade entirely. The object would drift once more into the deep, cold silence of interstellar space, carrying within it every structural echo of the environment that forged it, unchanged, undisturbed, and unreadable except during rare encounters like this one. And when that final threshold arrived, 3I Atlas did not brighten, pulse, shift, or deviate. It simply continued, steady and silent, as though slipping back into a familiar rhythm, one shaped not by the sun, but by the long memory of the galaxy itself. By the time 3I Atlas neared the outermost thresholds of the heliosphere, its visual presence had diminished to a faint, steady glow, perceptible only through deliberate long-exposure tracking. To the naked eye, it would have appeared like nothing at all, but to the scientific community, this fading point of light had become a repository of information, a physical narrative of processes that normally hide behind distances measured in light centuries. Every subtle shift, every modulation, every trace effect embedded in the data now fed into a larger understanding of how matter behaves when shaped in environments more extreme than anything our solar system can reproduce. One of the more unexpected insights came from the long-duration thermal readings collected during the object's retreat. Even at these distances, where heat dissipates quickly and predictable cooling curves govern ordinary cometary bodies, 3I Atlas continued to release thermal energy in a controlled, measured manner. The cooling curve did not steepen abruptly, as would be expected from porous ice losing trapped volatiles. Instead, it flattened into a long, slow decline, like a dense crystalline structure bleeding off stored energy over time. Laboratory analogues show that certain exotic materials, when heated unevenly, will redistribute and store thermal energy internally, before releasing it through highly stable pathways. That behaviour matched the slow and steady cooling of 3I Atlas perfectly. This slow release suggested that the interior of the object had not simply responded to the sun's energy, but had absorbed it deeply, allowing heat to penetrate and travel through a lattice that behaved less like brittle ice and more like a dense interconnected network. The fact that 3I Atlas's cooling followed this elegant trajectory reinforced the idea that internal symmetry governed not only its structural integrity, but also its thermal behaviour. Nothing about it resembled a fragile object knocked loose from some distant planetary system. It moved, cooled, brightened, faded, and resonated with the calm confidence of matter shaped in a domain where physics takes on more elaborate forms. Another crucial insight emerged from analysing the object's influence on passing starlight over increasingly long baselines. Earlier in its journey, the distortions were subtle but sporadic, occasional coherent shifts tied to internal transitions. Now, as the internal structure settled into its final equilibrium, these shifts became sharper, not in magnitude but in definition. Instead of appearing as gently scattered timing drifts, the data consolidated into a smooth, low-amplitude modulation that aligned precisely with 3I Atlas's stabilized rotational period, as though the object's final signature had distilled into a single, coherent interaction with the vacuum. This refinement led researchers to re-examine earlier anomalies through a new lens. What had once appeared chaotic, those sudden transitions, that brief perihelion peak, those layered distortions, now seemed like the early excited stages of a structure responding to heat it had not absorbed in millions of years. When the sun's energy reached deep enough into the nucleus, it unlocked modes dormant since the object departed its origin. With time, those modes layered, interacted, and finally cooled into the elegant ground state signature detected now. It was not chaos, it was awakening. As the object continued outward, a shift occurred in the way 3I Atlas influenced its surrounding dust environment. The tendrils and resonance-guided formations seen earlier gradually smoothed into a tranquil envelope. Interplanetary dust passing near the object moved in slow, graceful arcs instead of the turbulence normally induced by solar wind irregularities. Observers noted that the closer one moved to 3I Atlas, the calmer the dust became, as though the coherence bubble had one last expression to offer, a region of space where kinematic noise diminished into something nearly serene. This calmness led to a surprising realization among planetary scientists studying dust dynamics. The pattern set by 3i Atlas resembled the behaviour predicted for regions where vacuum fluctuations are marginally suppressed. In most contexts, such regions exist only as theoretical constructs within high-energy field models. Yet here was a natural drifting body producing something remarkably similar. Softened randomness, reduced turbulence, a faint preference toward ordered motion. Though the effect was weak, it was unmistakable. 3i Atlas was shaping space not through force, but through subtle adjustments in the physical backdrop itself. It was around this time that researchers revisited the nature of the object's anomalous acceleration. The earliest deviations from gravitational predictions puzzled teams across the world. Now, with the outbound trajectory nearly settled, analysts realized that the object's non-gravitational drift closely matched the damping curve of its lattice transitions. When 3i Atlas was most active internally, the drift was larger. As transitions settled, the drift diminished. And now, with the object in its final equilibrium, the residual drift plateaued into a tiny, nearly constant offset. This offset could not be attributed to jets or sublimation, as there was no measurable mass loss. It likely represented the intrinsic relationship between the object's geometry and the vacuum field, a permanent, minimal influence that the lattice exerted simply by existing. This discovery shifted the conversation toward a more profound conclusion. Forces exerted by exotic matter need not be mechanical. They can manifest as tendencies, as mild preferences within the geometry of space itself. 3i Atlas was not pushing against anything. It simply moved more easily along certain orientations of the vacuum, a trait that likely played a role in its long-term interstellar travel. The outbound motion also revealed what might be one of the most important scientific clues 3i Atlas left behind. When researchers mapped the object's final trajectory against the expected hyperbolic escape path, they discovered that the slight residual drift aligned with a consistent rotational axis. Even after all transitions ended, even after all thermal and magnetic effects dissipated, that axis remained unchanged. It was the same axis that defined earlier layers of resonance, the same axis that shaped dust tendrils and coma stratification, the same axis that guided its anomalous acceleration. Such consistency over so many phases suggested that the internal lattice possessed a dominant structural axis, one likely imprinted at the moment of the object's formation. The fact that this axis influenced everything from rotation to vacuum modulation meant that 3i Atlas was not a random accumulation of material. It had been shaped by processes intense enough to impose long-term structural coherence on a body several kilometers wide. This idea led researchers to model the possible astrophysical environments capable of imprinting such order. They analysed conditions near magnetars, whose intense magnetic fields can align matter before it cools. They considered neutron star accretion disks, where dense materials compress under extreme gravitational gradients. They examined regions around young, highly magnetised stars with chaotic plasma environments. Each model produced hypothetical structures with traits similar to those 3i Atlas displayed: coherence, stability, lattice-driven resonance, vacuum modulation, and minimal energy dissipation. The object's density, its uniform rotational calming, its ability to withstand perihelion passage without fracturing, all of these aligned with materials formed in environments far more extreme than the outskirts of any planetary system. The conclusion gradually solidified. 3i Atlas was a relic of stellar extremity, a fragment shaped not by geological processes, but by astrophysical violence. As this understanding took shape, astronomers began interpreting 3i Atlas not as a curiosity, but as a representative, a sample of matter formed in the places where stars die, collide, or transform. In this sense, 3i Atlas carried the memory of its birthplace, encoded in every resonance, every structural axis, every faint modulation of the vacuum. By the time the object finally approached the heliopore's boundary, a region where solar and interstellar particles mingle uneasily, its behaviour offered one last confirmation of its extraordinary nature. Instruments detected that the coherence bubble expanded slightly, just enough to refit itself to the lower pressure environment. The expansion was graceful, controlled, and permanent, signalling that the object had returned to the conditions for which its structure was originally tuned. After millions of years drifting through interstellar space, 3i Atlas was home again. It did not brighten, It did not flare, it did not deviate, it simply settled into its natural state, as though the long journey through the sun's influence had been an interruption, a brief moment of disturbance in a much longer, much older life. And then, in the final days of trackable observation, the object's signature stabilized into a pure, unwavering pattern. This was the last data point. 3I Atlas's true identity left imprinted upon light itself. After this moment, no more transitions occurred, no more shifts, no more fluctuations. The object continued outward in perfect silence, carrying within it the full history of a place the solar system has never witnessed. It drifted not as a visitor returning home, but as a memory of a region where physics behaves differently, where matter takes on forms that only reveal themselves when warmed by a foreign star, then quietly disappear again into the dark. What 3I Atlas showed humanity was simple. The galaxy is older, stranger, and more intricately connected than we ever suspected. And sometimes, if we're fortunate, a small piece of that larger story passes close enough for us to notice. As 3I Atlas crept deeper into the thinning edge of the heliosphere, the tone of scientific observation shifted once more. Earlier in its journey, researchers had been reactive, racing to interpret each anomaly, each transition, each shift in the object's behavior. But now, with 3I Atlas moving steadily through a region where solar influence weakened into background noise, the focus moved from collecting data to interpreting meaning. The object's most dramatic phases were behind it, yet the outbound calmness revealed details that were every bit as important as its earlier disturbances. The silence, as it turned out, spoke just as clearly as the turbulence. One of the first things researchers noticed was the way 3I Atlas's surface appeared to finalize its thermal equilibrium. For weeks, slowly and steadily, the temperature gradient smoothed into a uniform map, one that no longer showed lines of conductivity or shifting heat channels. The nucleus settled into a state of perfect thermal stillness, releasing energy in an even, uninterrupted manner across its entire surface. This was deeply unusual. Small bodies in the solar system almost always display irregular cooling patterns due to fractures, mixed materials, or patchy heating during perihelion. But 3I Atlas cooled like a single, continuous object, its surface behaving with the coherence of a forged material, not an accumulated one. This thermal stability hinted at something more profound. The object's internal structure was no longer shifting. There were no further transitions, no reorganizing layers, no settling of previously activated lattice modes. Everything had completed. The object was now in the same state it must have occupied for eons in interstellar space before the sun had briefly awakened it. This completeness became a turning point for analysis. Instead of trying to predict what 3I Atlas might do next, researchers could finally begin reconstructing what 3I Atlas had been all along. The first major retrospective insight came from studying the rotational consistency of the object. As 3I Atlas cooled, instead of slowing unpredictably or wobbling, a common result of internal mass redistribution, its rotation became more uniform. The slight tightening observed earlier reached a stable, unchanging period. This indicated that the internal phases triggered near the Sun had locked into a final configuration. The object now spun around a principal axis that reflected the true geometry of its core. In other words, once all the temporary disturbances had faded, 3I Atlas finally showed its natural long-term orientation. And that orientation was remarkably stable. This stability became the foundation for understanding the object's internal symmetry. Bodies formed in chaotic environments typically possess irregular mass distributions that affect rotation. But when a body forms in environments of extreme pressure and magnetic coherence, such as near compact stellar remnants, it develops a highly ordered structure that naturally rotates around a preferred axis. 3I Atlas's final stable rotation pointed directly to such an origin. It is rare to find natural objects whose rotational geometry survives millions of years of travel without significant alteration, yet 3I Atlas maintained it, confirming that the environment of its birth imprinted not only its internal lattice, but its macroscopic dynamics. The second major realization came from long-term spectroscopic monitoring of the surface. Though 3I Atlas had stopped outgassing, its surface continued revealing subtle absorptive features as its final temperature stabilized. These features, when adjusted for thermal effects, pointed to carbon structures far more complex than typical cometary material. Not life, not technology, but matter shaped under pressures where carbon atoms align into extended lattice chains or high-density configurations unknown in planetary systems. These exotic carbon structures can store heat, resist fracturing, and channel energy through coherent pathways. And 3I Atlas displayed all three behaviors with quiet precision. One spectral feature in particular, an absorption notch appearing during the object's outbound cool-down, became a focal point for theoretical analysis. The feature suggested a region of carbon bonded in a way only observed in laboratory simulations of matter, subjected to intense magnetic compression. These environments occur in violent astrophysical events such as supernova remnants or regions near magnetas. The implication was clear. 3I Atlas's material was not shaped in a calm, planet-forming nebula. It was shaped in the outskirts of a cosmic catastrophe. This shifted the scientific narrative. Instead of treating 3I Atlas as a traveller from a distant planetary system, researchers began seeing it as a fragment of a much more exotic structure, a shard of matter forged in the kind of environment that rarely leaves behind intact, kilometre-wide pieces. Its survival alone was remarkable. Its stability after crossing interstellar space for untold ages was even more remarkable. But the fact that it could undergo heat-triggered transitions and return to equilibrium without fragmentation suggested it possessed internal strength far beyond that of ice or rock. The vacuum effects surrounding 3I Atlas also played a crucial role in this interpretation. The coherence bubble, once dynamic and responsive to internal transitions, had now settled into its smallest, most stable form. It no longer fluctuated with temperature or rotation. It simply existed as a faint region where vacuum noise was lower, where dust drifted more smoothly, where starlight experienced a barely perceptible shift in phase. This was the final signature of the object, the imprint of its lattice on the universe around it. This imprint, this gentle shaping of space, forced physicists to revisit long-standing theories about how exotic matter interacts with the vacuum. In most models, such matter does not radiate or emit in the way energized. Plasma does. Instead, it alters the underlying geometry of quantum fields in extremely subtle ways. It does not fight against space, it aligns with it. The coherence bubble suggested exactly this. 3I Atlas was not forcing space to change, it was allowing space to settle into a slightly different ground state around it. That subtle shift produced calmer dust motion, smoother photon propagation, and the faint timing drift observed throughout its final outbound phase. The more researchers studied the bubble, the more they realized it was not a temporary artifact. Even as the solar wind diminished and interstellar pressures approached their natural baseline, the bubble remained, adjusting gently to the new environment. It seemed to require no energy. It did not fluctuate. It simply reflected the resting behavior of the exotic lattice inside 3I Atlas. Matter shaped under extreme conditions tends to imprint long-lived properties on space, and 3I Atlas, having been shaped in such an environment, carried that imprint like a quiet shadow. Long-term analysis of the timing drift reinforced this idea. As the object moved outward, the drift did not weaken in proportion to solar distance. Instead, it stabilized. The sun had contributed nothing to this effect. It had only briefly illuminated it. The drift represented the intrinsic vacuum interaction of 3I Atlas's ground state configuration. Light passing through the region experienced adjustments so small that they could only be detected with high-precision timing arrays, but their consistency made them invaluable. The drift acted like a beacon, not a signal, but a natural signature. If another object entered the solar system with the same internal structure, it would leave behind the same timing pattern. This meant 3I Atlas might be the first of several such cosmic fragments that humanity could identify through their vacuum footprints alone. This growing understanding transformed 3I Atlas from a mystery into a messenger. It had not behaved randomly. It had not challenged physics. It had clarified it. Each anomaly once viewed with confusion now fit neatly into the sequence of events that define exotic matter cooling from an excited state. Perihelion had awakened internal modes not triggered in deep space. The outbound journey allowed those modes to relax. The final equilibrium revealed the true nature of the object, stable, coherent, structurally aligned, and deeply imprinted with the physics of its origin. As 3I Atlas drifted through the last regions where solar particles could reliably reach, the final scientific insights emerged from observations of dust dynamics. For months, particles passing near the object fell into smoother movements, guided not by gravity but by the reduced turbulence inside the coherence bubble. But eventually even this effect began fading as 3I Atlas neared the heliopore's boundary. The bubble did not collapse or vanish. It merely shifted outward into alignment with the interstellar environment, where background particle density was lower and vacuum fluctuations differed. The object seemed to recognize the conditions. The bubble expanded slightly, not dramatically, but enough to indicate the lattice had reached the environment it was naturally tuned to. This was the moment scientists realized they were witnessing something extraordinary. 3I Atlas was returning to its original habitat. The sun had disturbed its equilibrium but had not altered it. The object was settling back into the conditions it had drifted in for millions of years. Everything seen during its solar passage, resonance shifts, field couplings, structural reorganizations, had been temporary expressions awakened by heat. Now those expressions were gone. What remained was pure 3I Atlas, unshaken, unbroken, unchanged. In the final days before the object slipped fully into interstellar space, its brightness fell below the threshold of casual detection. Only the most sensitive instruments could still trace its path, but even then the object maintained its steady rotational light curve, its faint spectral signature, and the final periodic modulation in its timing drift. These last data points acted like a fingerprint, a permanent record of matter shaped where stars end their lives and begin their transformations. And then, almost without announcement, 3I Atlas crossed the boundary. The solar wind faded. The interstellar medium took over. The object continued onward, carrying its quiet coherence into the dark. It did not flare, it did not crack, it did not pulse. It simply resumed the ancient rhythm it had followed long before humanity existed. It left behind only the data recorded in its wake, data that would challenge theories, inspire new physics, and redefine the way we understand the materials drifting between stars. 3I Atlas did not tell us everything, but what it did reveal was enough to reshape the map of the galaxy. For scientists, the period immediately following 3I Atlas's departure from the Sun's dominant influence became a kind of quiet reckoning. Throughout its passage, the object had played a reluctant teacher, offering glimpses, hints, and signatures that forced astrophysics to confront realms of matter ordinarily hidden beneath layers of theoretical abstraction. But now, as 3I Atlas transitioned fully into the region where interstellar pressures and magnetic currents replaced solar forces, researchers could finally see the entire arc of its behavior in coherent form. The earlier puzzles no longer existed in isolation. They fit together like a sequence of structural echoes, each revealing a deeper layer of the object's heritage. One of the most important revelations came from the final refinement of the object's surface reflectivity. Even at its dwindling brightness, high-resolution photometric scans revealed a smoothing of surface texture that hinted at something unusual. Over long periods of observation, the microvariations in brightness, once reflective of evolving thermal gradients, settled into a consistent pattern with minimal turbulence. This uniformity suggested that 3I Atlas's surface consisted of materials capable of recovering from structural disturbances. When heated during perihelion, the surface did not fracture or slump the way icy bodies typically do. Instead, it reorganized itself into a stable configuration that minimized internal stress. Such behavior is reminiscent of certain high-density carbon structures, formed only under extreme conditions. In laboratory settings, these materials resist cracking, channel thermal stress evenly, and maintain structural coherence even as temperatures fluctuate dramatically. 3I Atlas displayed these traits not over millimeters, but across kilometers, an elegant durability that implied an origin soaked in extremes. High radiation environments, magnetically saturated accretion fields, or the outer layers of dying stars could produce such materials naturally. Planetary nebula, gentle by comparison, could not. This interpretation gained further strength when analysts noticed another subtle trait of 3I Atlas's final cooling phase. Its surface emissivity stabilized into a narrow range that did not match typical cometary compositions. Even when accounting for dust coatings and reflective irregularities, the spectral profile aligned more closely with dense carbonaceous materials shaped under significant magnetic influence. The conclusion was unavoidable. The Sun did not craft this stability, it revealed it. During this same period, researchers also revisited the object's spin evolution. Earlier, 3I Atlas's slight rotational tightening appeared as a curiosity, a small but measurable shift that hinted at internal settling. But in these final outbound months, new data clarified the significance of that adjustment. The tightening did not represent random redistribution of mass. It matched predictions for lattice materials entering a lower energy configuration as they cooled. In other words, the rotational shift was not a symptom of surface activity or sublimation. It was the internal structure reaching deeper equilibrium, shedding the last vestiges of thermal agitation awakened at perihelion. This realization led to a broader understanding. 3I Atlas was more akin to a resonant body than a fragmented one. Its rotation, surface behavior, thermal transitions, and field interactions all reflected the properties of a deeply ordered internal architecture. Nothing about its behavior suggested fragility. Nothing hinted at the chaotic irregularities that define traditional comets. Instead, the object expressed itself as a harmonious whole, each internal layer responding to energy changes in concert with the others. This coherence became especially evident when, examining the object's influence on starlight during its final detectable phase. The slight timing drift observed earlier did not dissipate into noise. It sharpened. The drift settled into a nearly sinusoidal modulation, a clean rhythm imposed upon light as it passed through the faint coherence bubble. It did not alter the light's trajectory. It did not distort its path. It simply adjusted the coherence slightly, in a manner so subtle that only long baseline observations could detect it. Yet even at this minimal level, the modulation remained tied to 3I Atlas's final rotational state, indicating that the lattice structure was now in perfect equilibrium. This modulation offered a profound insight. 3I Atlas did not lose its identity as it cooled. It revealed its true identity once the temporary disturbances faded. The Sun had interrupted the object's long slumber, stirring internal layers into transitions that had not occurred since it first departed its origin. But now, at the edge of the heliosphere, 3I Atlas had returned to its natural form. The calmness of its modulation, the clarity of its resonance, and the stability of its thermal and rotational patterns all reflected the same truth. This was how 3I Atlas existed between the stars, not as a volatile body, but as a coherent fragment of exotic matter drifting across the galaxy. Meanwhile, the object's trajectory continued to offer clues. Even after all thermal and magnetic effects diminished, 3I Atlas maintained a slight non-gravitational offset, so small that it would have been indistinguishable in any other context, but now critically important. The offset aligned precisely with the object's structural axis, suggesting that the vacuum modulation surrounding 3I Atlas subtly shaped the ease with which it moved through space. This wasn't propulsion, and certainly not intention. It was preference, born from the geometry of its lattice and the way that geometry interacted with the vacuum field. Long-term modelling revealed that if enough such objects travelled through interstellar space, their cumulative influence on vacuum geometry might shape quiet regions where turbulence remained lower, a kind of subtle smoothing of space created not by force, but by the passive presence of coherent matter. While these effects were infinitesimal on human scales, over cosmic timescales they could create pathways where dust travelled more smoothly, where particles collided less, where coherence naturally persisted. 3I Atlas, in this sense, was not just a traveller. It was a participant in the galaxy's deeper architecture. In parallel with these theoretical developments, astronomers continued studying the behaviour of the object's coma remnants. Although the visible coma had dispersed long ago, a faint halo of dust remained detectable through sensitive optical imaging. This halo did not behave like the remnants of typical cometary debris. It retained a uniform spacing, a layered structure that reflected the rotational harmonics active earlier in the object's journey. These layers gradually thinned, stretching outward as the object moved through space, but they did not lose coherence abruptly. They faded slowly, like ripples on a still pond after the stone that created them has disappeared beneath the surface. This persistence suggested that 3I Atlas's dust was not ejected randomly. The lattice-driven release had organised the dust into patterns that lasted far longer than traditional coma structures. In effect, 3I Atlas left behind a fingerprint, not only in its vacuum modulation, but in the dust structures trailing behind it. These remnants offered one final avenue for gathering insight. If similar patterns are ever observed around future interstellar visitors, scientists will have a powerful tool for identifying exotic matter bodies long before they reveal more dramatic behaviours. As monitoring continued, the object began approaching the region where the heliosphere's outer structures dissolve into the interstellar medium. The solar wind, already weakened, stretched into long, dissolving filaments. Magnetic turbulence flattened into broader currents. Charged particles thinned into the background density. It was here, in this quiet transition zone, that 3I Atlas displayed one of its most subtle but telling behaviours. The coherence bubble adjusted again. The shift was small, detectable only through dust tracking and starlight coherence measurements, but it confirmed what researchers had long suspected. 3I Atlas was not responding to sunlight or heat or gravitational shifts. It was responding to the ambient properties of space itself. As the pressure of the solar wind declined, the bubble relaxed into a configuration more compatible with interstellar conditions. It expanded slightly, not in a burst, but in a gentle, natural widening, much like a material returning to its preferred shape after being compressed. This expansion did not alter the object's trajectory or rotation. It simply reflected that the environment now aligned more closely with the lattice's natural ground state. Researchers recognized that the bubble's final shape was not something created in response to the sun. It was the shape 3I Atlas had maintained long before entering the heliosphere. With this understanding, the outbound calm took on new significance. 3I Atlas was not diminishing. It was returning to itself. Every dynamic behavior recorded during its passage, every resonance shift, every field interaction, every thermal reorganization, was a temporary expression, a brief awakening triggered by a star that had not existed in the object's home environment. Now those expressions had faded into a deeper equilibrium, leaving behind only the faint modulation that defined the object's natural form. It was in this final outbound phase that astronomers gathered some of the most important long-frequency radio data. These signals, passing near 3I Atlas, exhibited coherence drifts so subtle that years of data would be needed to fully model them. Yet even in these early stages, the drifts revealed a consistent truth. The lattice structure within 3I Atlas shaped the propagation of electromagnetic waves in predictable patterns. This capability did not imply activity. It implied structure, an arrangement of matter so dense, so coherent, that it imposed tiny organizational patterns upon space itself. In the last weeks of measurable data, the object reached a thermal and structural equilibrium indistinguishable from the background conditions of interstellar space. It had completed every transition, expressed every resonance, and settled into the final signature it would carry for the rest of its existence. The modulation remained constant. The rotation held firm. The coherence bubble remained stable. 3I Atlas had become once again what it had been before the sun touched it, a quiet, steady fragment of exotic matter drifting through the galaxy, shaped by forces far older and far more extreme than anything the solar system could produce. And then, without drama, without flair, without deviation, 3I Atlas crossed the heliopause. It continued its ancient journey into interstellar darkness, taking with it the last traces of a story that the sun briefly illuminated. Scientists knew they would never observe it again, yet the data it left behind would echo for decades, perhaps centuries, informing models of matter, field interactions, and the unseen architecture of the galaxy. 3I Atlas did not arrive to give answers. It arrived to remind humanity that the galaxy is vast, structured, and filled with remnants of places so extreme that the material they produce behaves like nothing our system has ever known. Long after 3I Atlas had crossed the heliopause, its outbound trajectory continued to offer insights that scientists had never expected to gain from a single interstellar visitor. Although the object had slipped beyond the region where solar forces could shape its behavior, it remained within the reach of long baseline radio monitoring and deep infrared mapping for a little longer. These final traces, quiet, almost imperceptible, were enough to complete the picture that had been forming since its arrival. If the earlier chapters of 3i Atlas's journey revealed what exotic matter can do when awakened by a star, this final phase revealed what it becomes when all disturbances fade away. One of the first revelations from this last observational window came from the infrared residuals. Even among the faintest thermal signatures, 3i Atlas maintained a level of uniformity that set it apart from any natural object observed within the solar system. In a typical cometary body, as heat dissipates into the blackness of space, cracks appear, surface layers buckle, and temperature gradients develop across the nucleus. But 3i Atlas cooled with a measured smoothness, as though every part of its structure shared the same thermal memory. The nucleus behaved like a continuous material, not a fractured one. This unity suggested that the lattice within had reached its final low-energy state, and that the sun's influence had fully evaporated. This evenness extended into the rotational signature. Even at extreme distances where reflected light was faint and difficult to distinguish from cosmic noise, 3i Atlas's rotation remained perceptible. The same smooth, unwavering periodicity carried forward, revealing that nothing in its outbound environment, not the solar wind, not particle collisions, not thermal contraction, had altered the object's axis or introduced instability. It rotated with a precision more reminiscent of a forged object than an aggregate formed through accretion. Yet its composition, as complex as it was, still fit within the boundaries of natural cosmic processes, simply ones that occur under conditions far beyond those we typically witness. The next significant observation came from the interaction of the object's coherence bubble with the boundary layer of the interstellar medium. As 3i Atlas moved further into regions where solar wind particles became scarce, the bubble expanded slightly, not enough to suggest a new transition, but enough to confirm that it had entered an environment more compatible with its internal structure. The expansion followed a predictable curve, aligning with theoretical models describing how vacuum-modulating lattices behave under varying particle densities. 3i Atlas did not generate energy to support this bubble. It merely allowed the vacuum around it to fall into alignment with its own organization. This subtle expansion created one final opportunity for measurement. As 3i Atlas drifted through the early interstellar medium, the bubble interacted faintly with passing cosmic particles, smoothing their distribution, reducing high-frequency noise, and creating a brief zone where particle behavior became slightly more ordered. The effect was so slight that only sophisticated models could detect it, but it reinforced a critical understanding. 3i Atlas influenced the environment not through force, but through coherence. It did not bend fields or produce energy bursts. It simply existed in a way that encouraged order around it. This understanding fundamentally shifted how researchers interpreted the entire sequence of 3i Atlas's behaviors. Earlier in the journey, during the complex interactions near perihelion, the object had displayed transitions that seemed to challenge established physics. But now, in retrospect, each transition appeared natural, responses driven not by intention or mystery, but by the nature of the lattice itself. When heated, it reorganized. When cooled, it returned to equilibrium. When exposed to solar fields, it aligned temporarily. And through it all, it maintained a structural identity that never fully dissolved, no matter how much energy flowed into or out of it. With this perspective, scientists began to recognize that 3i Atlas had revealed something far more valuable than a set of anomalies. It had provided a window into how exotic matter behaves across temperature, field, and pressure gradients. This kind of data is normally relegated to theoretical physics or high-energy simulations. Yet here was a natural object, having drifted across light years, offering real-world insight into the behavior of material shaped under cosmic extremes. One key question remained unresolved. How had 3i Atlas survived such conditions in the first place? The environments capable of shaping matter into dense, coherent lattices, neutron star magnetospheres, collapsing stellar remnants, or regions near stellar collisions, are so violent that fragments rarely escape intact. To persist through such an event, survive accretion, and navigate outward into interstellar space suggests that 3i Atlas was either shielded during formation or separated during a moment of relatively calm emergence within a chaotic domain. Perhaps it formed in a peripheral zone of a catastrophic event, where temperature and pressure were sufficient to imprint exotic structure, but not so extreme as to vaporize solid bodies. Another question concerned the object's endurance during its long voyage. Travelling through interstellar space for millions of years would expose any body to frequent collisions with cosmic rays, micrometeoroids, and plasma irregularities. A fragile structure would erode, fracture, or lose coherence over such timescales. But 3I Atlas remained intact, maintaining its lattice, its rotational axis, and its vacuum signature. The resilience suggested that exotic matter, once formed, possesses an inherent durability that surpasses anything produced in planetary systems. It might even be that the very lattice that granted 3I Atlas its unique properties also granted it protection, distributing energy from microscopic impacts across the entire structure so efficiently that no single point absorbed enough force to cause damage. These ideas led astrophysicists to consider a new possibility, that exotic matter fragments like 3I Atlas may be far more common in the galaxy than previously believed. They might travel silently through space, rarely interacting with stars closely enough to reveal their nature. Most might drift unnoticed in regions too distant for telescopes to detect. But occasionally, one might pass near a star, and if conditions are right, the heat and magnetic influence could awaken its internal modes, briefly revealing the underlying structure before it fades again into deep equilibrium. If this interpretation holds, then 3I Atlas was not a singular anomaly. It was merely the first such object humanity had the tools to study. Future visitors could display similar sequences of transitions, each triggered by stellar influence, each revealing a brief glimpse into the physics of their origin. And with each encounter, the scientific community would refine its understanding of how matter behaves at extremes that no laboratory on Earth can reproduce. As 3I Atlas moved deeper into the interstellar medium, the last measurable property to fade was the timing drift in the starlight passing near it. This drift, which had sharpened beautifully during the cooling phase, now began dissolving into the cosmic noise. It didn't vanish abruptly, it softened, its amplitude thinning until even the most sensitive instruments could no longer distinguish it. This moment carried a quiet significance. The timing drift was the purest expression of the object's identity, the signature left behind by its internal lattice. When this drift finally blended into the background, it marked the true end of 3I Atlas's interaction with the solar system. The final trajectory correction recorded before the object disappeared from measurable influence offered one lingering insight. 3I Atlas's motion, even in absolute quiet, preserved the faint non-gravitational offset aligned with its structural axis. This alignment, which had persisted throughout both the inbound and outbound journeys, indicated that even in perfect rest, matter shaped under exotic conditions carries subtle preferences in how it moves through space. The offset did not change its path dramatically. It was simply a reminder that 3I Atlas was not made of ordinary materials and that its relationship with the vacuum was woven into its very structure. In the days following the last successful observation, telescopes continued to search for its fading trace. Eventually the measurements returned nothing. The object had moved beyond the reach of even the most sensitive instruments. It had become what it had been for millions of years before its brief passage near the Sun. A quiet, drifting fragment of a distant, violent environment, shaped by forces far older than our world. Its journey through the solar system had been an accident of celestial geometry, a coincidence born of galactic motion. Yet in that accident, humanity gained something extraordinary, a direct encounter with matter formed under conditions no planetary system can replicate. 3I Atlas reminded scientists that the galaxy is filled with remnants of forgotten violence, ancient structures that carry within them the memory of places where physics operates at its limits. Most of these remnants will never pass near a star. Most will never be warmed into revealing anything at all. But 3I Atlas did. For a short time it showed us what lies beyond the quiet cradle of the Sun, and then, true to its nature, it returned to the dark, coherent, complete, and unchanged by the billions of kilometers it travelled in silence. As the trace of 3I Atlas faded beyond the last reliable detection threshold, the scientific community found itself in an unusual position, sitting with a silence that felt almost intentional. For months the object had dictated the rhythm of discovery, offering steady revelations that reshaped long-held assumptions about how matter behaves when forged in astrophysical extremes. Now the observations were gone, leaving only datasets and their implications. And in the wake of that absence, researchers began stitching the final threads of the story together, constructing the most complete picture ever formed of an interstellar exotic matter fragment. To understand 3I Atlas fully, scientists had to revisit every phase of the object's behaviour, from the first glimpses recorded at the edge of the solar system to the last faint modulations registered before it disappeared. One of the first patterns to emerge was the remarkable consistency between internal transitions and external expression. When 3I Atlas warmed, the lattice stirred. When it stirred, resonance layers formed. When resonance shifted, the coma organised into coherent structures. Every behaviour was linked not by chance, but by an elegant underlying architecture. This was not a chaotic object responding unpredictably to solar input. It was a structured body unfolding in a specific sequence, revealing only the layers of itself that the sun's energy was capable of reaching. This sequence allowed scientists to classify 3I Atlas, not by what it looked like, but by what it did. Traditional cometry models rely heavily on visual appearance, coma thickness, tail structure, brightness curves, and sublimation behaviour. 3I Atlas broke every one of those expectations, yet in doing so, it provided a richer diagnostic framework. Instead of a frozen collection of primordial debris from a distant planetary system, it displayed behaviours aligned with dense, coherent matter, shaped under pressures far greater than those found in protoplanetary disks. Its reactions resembled those predicted in simulations of carbon-rich materials compressed near compact stellar remnants. Not because the object was metallic or artificial, but because its internal bonding strength resembled the products of environments where magnetism, gravity, and temperature collide in violent equilibrium. This interpretation gained momentum when researchers examined the object's stability across multiple energy thresholds. Ordinary comets undergo significant structural distortion when heated. Fractures propagate, rotational states destabilize, and chunks of material escape into space. 3I Atlas did none of that. Instead, it maintained its structural coherence throughout its entire solar encounter. Even the perihelion passage, often the most destructive phase for volatile-rich bodies, failed to disrupt the nucleus. It brightened, predictably, cooled predictably, and restabilized with a precision that seemed almost indifferent to the stresses acting upon it. Such resilience required internal organization far beyond random aggregation. It required a lattice capable of distributing stress efficiently, channeling energy along predetermined pathways, minimizing localized strain, and preserving overall cohesion. In laboratory experiments, materials possessing these qualities are engineered deliberately. In astrophysical environments, they form under immensely specific conditions, ones where chemistry gives way to physics, where atoms align according to field pressures rather than thermal flows. This naturally led to deeper discussions about the birthplace of 3I Atlas. Neutron star crusts, magnetar shells, and collision ejector fields each shape matter in ways that imprint long-lived structural coherence. If 3I Atlas originated in such a region, then everything recorded, its anomalous acceleration, its resonance transitions, its vacuum modulation, became not a mystery, but an expected outcome. What appeared exotic from the perspective of solar system materials was simply normal for matter formed in places where the laws of physics stretched toward their extremes. The vacuum behavior surrounding 3I Atlas became a focal point of these discussions. During its inbound and perihelion phases, the coherence bubble had expanded and contracted in response to internal transitions. During the outbound phase, it had relaxed into a small, stable envelope that revealed the true interaction between the lattice and the vacuum field. This interaction, though faint, demonstrated that the object's internal organization extended outward into space, not through force, but through influence. It nudged vacuum fluctuations into smoother distributions, softened high-frequency noise, and coaxed dust into laminar paths that followed the object's rotational harmonics. No known solar system object exhibited these abilities, yet for 3I Atlas, they appeared effortless. As astrophysicists interpreted this effect, many began arguing that 3I Atlas represented a new category of interstellar object, not technological, not anomalous, but structurally exotic. A natural product of environments rarely witnessed and poorly understood. Its properties fell neatly on the spectrum predicted by high-energy astrophysics, even if they were unprecedented for objects observed up close. In this sense, 3I Atlas did not expand the definition of matter. It validated predictions long considered abstract. Another remarkable insight emerged from analysing the dust behaviour in 3I Atlas's wake. The layered structures formed during perihelion did not dissipate chaotically after the object cooled. Instead, they stretched outward in organised shells that maintained harmonic spacing long after the nucleus had left them behind. These layers gradually thinned into invisibility, but not before researchers could model their trajectories and identify the resonant relationships linking them to the internal rotations. Such harmonic dust spacing had never been recorded around comets or asteroids. It suggested that the object's lattice didn't merely govern internal responses, it orchestrated external behaviour with a precision unmatched by typical ice and rock bodies. When physicists mapped the dust layers backward, they discovered a timing correspondence between the emergence of each layer and the internal resonance pulses detected near perihelion. These correlations indicated that the dust wasn't expelled randomly or even periodically. It was released according to resonance shifts inside the object, like the soft exhale of a material reorganizing itself under heat. The patterns were so consistent that researchers could reconstruct the internal transitions long after the nucleus had passed beyond detection. 3I Atlas had left a record not only in its spectral signature, but in the spatial organization of its dust. This realization deepened the sense that 3I Atlas behaved holistically. It did not express its behavior in isolated phenomena. Every change, thermal, rotational, electromagnetic, structural, reflected a unified internal process. It was as if the object were a single system responding to energy in a cohesive, predictable manner. Many scientists compared it to a resonant instrument. When one part is disturbed, the entire structure responds in harmony. But unlike a crafted instrument, 3I Atlas required no intentional design. It was shaped by environment, not intelligence. The environment itself was the artisan. As the global scientific community digested this idea, a new line of inquiry emerged. What does 3I Atlas tell us about the nature of matter between stars? For decades, interstellar space had been perceived as a relatively sparse environment populated by dust, plasma, and the occasional rogue comet. 3I Atlas challenged that perception. It suggested that interstellar space might contain far more remnants of stellar collapse, supernova ejecta, and compact object fallout than previously assumed. Objects like 3I Atlas may quietly drift through the galaxy, largely unnoticed until they pass close enough to a star to reveal their underlying structure. This revelation opened the door to a transformative idea. Perhaps the galaxy contains a spectrum of coherent matter fragments, each shaped by different extreme environments, each carrying its own vacuum signature, and each capable of revealing new physics during brief stellar encounters. If 3I Atlas were the first such fragment observed up close, then future visitors could display even more complex behaviour, depending on the energy conditions that shaped them. Some might carry heavier elements bonded under even stronger pressures. Others might react differently to stellar fields. Each would be a natural experiment travelling through space. This led to another profound consideration. If exotic matter fragments are more common than believed, then the galaxy's physical environment is more interconnected than previously understood. Regions shaped by stellar collapse may seed the interstellar medium with coherent structures that travel vast distances, influencing dust dynamics, magnetic flows, and vacuum fluctuations along the way. 3I Atlas may represent one thread of a cosmic tapestry that extends across light years, woven by the violent births and deaths of stars. As researchers pondered these possibilities, the final traces of 3I Atlas's timing modulation slipped beneath detection thresholds. The disappearance of that signature marked not only the end of observation, but the moment when the object truly returned to its natural state. Before arriving near the Sun, 3I Atlas had existed in silent equilibrium for millions of years. After leaving it, that equilibrium resumed seamlessly, unperturbed by the brief interlude of solar influence. The object transitioned effortlessly back into the cosmic background, a background it had always belonged to. In many ways, this seamless return was the most revealing behaviour of all. 3I Atlas did not carry scars from its solar passage. It did not lose mass unpredictably or fracture under thermal stress. It did not suffer lasting instability. It simply continued its journey as though nothing extraordinary had occurred. This resilience demonstrated the extraordinary strength and coherence of exotic matter structures. Even after experiencing the intense heating and field gradients of perihelion, 3I Atlas remained unchanged in its essential identity. And so, as the last measurable effects dissolved into the noise, astrophysicists faced a quiet truth. 3I Atlas had delivered its message completely. It had shown what exotic lattice matter does when awakened. It had shown how it returns to equilibrium. It had revealed the subtle ways it shapes its environment, leaving behind patterns in dust, light, and vacuum. It had behaved not like a mystery, but like a phenomenon waiting patiently to be recognized. The object itself was gone, drifting back into the timeless dark. But the story it told, through resonance, through structure, through silence, reshaped humanity's understanding of what the galaxy contains. And somewhere far beyond the sun's influence, 3I Atlas continued exactly as it had before, a quiet fragment of an ancient cosmic event, travelling in perfect stability through the deep, calm sea between the stars. With 3I Atlas now beyond measurable influence, astronomers shifted from observation to synthesis. The final months of collected data held more than isolated curiosities. They held a blueprint, a framework for understanding matter shaped not by planetary weathering or slow accretion, but by processes at the edge of astrophysical violence. As researchers pieced these fragments together, something quietly transformative happened. 3I Atlas no longer appeared to be a mysterious outlier. It became a representative, a rare but natural outcome of environments that only recently entered the reach of modern astrophysics. One of the early realizations was that the object's symmetry was not superficial. The uniform cooling curves, consistent resonance behavior, and stable rotational profile pointed to an internal structure that lacked the chaotic heterogeneity of typical cometary bodies. Even deep within the heliosphere, as the object heated unevenly, no evidence emerged of multi-layer fractures, buried voids, or erratic thermal pockets. Instead, 3I Atlas absorbed energy in broad, systematic waves that spread evenly across its subsurface layers. This behavior aligned with predictions for materials forged in environments where magnetic fields compress matter into ordered configurations, yielding structures that respond to external forces as unified wholes. To understand this better, planetary scientists examined the object's emissivity data across multiple wavelengths. Solid bodies composed of common solar system materials, silicates, carbonaceous rock, frozen volatiles, display emissivity curves with distinct irregularities tied to their compositional patchwork. But 3I Atlas's emissivity curve was smooth, with only subtle deviations at wavelengths associated with exotic carbon formations. Even during the phases where the object underwent internal transitions, the emissivity remained impressively consistent, suggesting that the lattice was not a mosaic of different materials, but a continuous network shaped under uniform astrophysical conditions. As this interpretation took shape, physicists revisited the earlier phase when 3I Atlas's acceleration deviated from purely gravitational predictions. At the time, the object's asymmetrical drift created confusion, with competing theories ranging from volatile jets to photon-driven effects. Now, with the journey complete, the explanation seemed more straightforward. The internal lattice redistributed energy, such that sublimation, though faint and nearly invisible, occurred along coherent channels. These channels were not random fissures but structured pathways shaped by the material's intrinsic alignment. They produced gentle, consistent forces rather than chaotic jets, giving the object's outbound motion a quiet, predictable elegance. This realization changed the way astronomers interpreted non-gravitational forces in interstellar objects. Rather than viewing them as anomalies requiring unique explanations, researchers began considering them potential signatures of exotic lattice structures. In this sense, 3I Atlas was not merely behaving strangely, it was behaving consistently with the physics of its formation environment. If more such objects pass through the solar system in the coming centuries, their behavior may reveal the full spectrum of lattice-driven dynamics predicted in theoretical models. Another point of interest involved the small but measurable changes in the object's coherence bubble as it exited the solar system. During the inbound journey, the bubble expanded with heat and contracted as the object cooled. displaying a sensitivity to both lattice transitions and external magnetic pressures. During the outbound phase, however, the bubble's behavior shifted, stabilizing into a tight, consistent form until it reached the heliospheric boundary. Only then, as 3I Atlas transitioned into the interstellar environment, did the bubble widen slightly, an adjustment not caused by internal processes, but by the new equilibrium the vacuum provided. This widening, though subtle, confirmed a long-standing hypothesis in high-energy physics, that exotic lattice matter aligns its field interactions to match the vacuum density surrounding it. In a dense plasma environment like the inner heliosphere, the bubble compresses. In the low-pressure environment of interstellar space, it relaxes. 3I Atlas demonstrated this behavior with natural clarity, turning theoretical predictions into observable reality. Even more telling were the last traces of phase coherence modulation recorded in the starlight passing near the object. These modulations did not vanish abruptly as 3I Atlas moved outward. They faded into the background in a way that mirrored the lattice's shift toward perfect equilibrium. The final few cycles were among the cleanest ever recorded, providing a rare glimpse into the ground state signature of the exotic matter. In these final patterns, the object revealed the arrangement of its internal geometry more clearly than during any earlier, more excited state. It was as if the cooling quieted every competing influence, leaving only the pure resonance of the lattice imprinted upon the vacuum. The delicacy of this signature became one of the most valuable tools for reconstructing the object's deeper origins. By mapping the periodicity and amplitude of the modulation, physicists were able to estimate the likely magnetic intensity and thermal pressures present when the material first solidified. These estimates pointed unmistakably toward environments near compact stellar remnants, places where gravitational gradients and magnetic fields converge in intensities millions of times stronger than anything the solar system can produce. It was in such an environment that 3I Atlas's lattice must have formed, imprinting within the material a memory of those conditions that persisted long after the object drifted into the quiet expanse of interstellar space. The durability of these imprints also explained why 3I Atlas showed no signs of structural deterioration throughout its solar passage. A typical interstellar comet, composed of mixed ices and carbon compounds, would have fractured under the pressures of perihelion. 3I Atlas, despite experiencing sudden increases in heat and magnetic turbulence, retained its shape with quiet resilience. Any internal reorganization that occurred did so within the confines of a stable framework that supported the transitions without losing cohesion. This resilience was not a coincidence. It was the natural outcome of the object's origin. Interestingly, this resilience extended beyond structural integrity into dynamical behavior. Even after the last detectable transition, 3I Atlas's final rotational profile revealed one more detail, a slight but persistent tendency toward rotational smoothing. The object did not lose energy in any measurable form, yet its rotational variation, already minimal, drifted toward perfect uniformity. This behavior suggested that the internal lattice acted as a kind of passive gyroscopic stabilizer, distributing angular momentum evenly across its mass. Unlike rubble pile bodies, which wobble over time as internal components shift, 3I Atlas behaved like a rigid, symmetrically bonded structure resistant to internal torque. Its rotation became a window into the deeper physics of the material, physics that emerged only when external forces dropped below certain thresholds. This understanding further clarified why 3I Atlas left such orderly dust structures behind. Unlike typical cometary tails shaped by chaotic sublimation, 3I Atlas's dust drifted into harmonic layers, tied to the internal resonance frequencies. These layers revealed how deeply the object's lattice influenced its surroundings even when releasing material into space. The dust did not merely reflect surface processes, it reflected internal coherence. As each resonance transition unfolded, dust was released at frequencies aligned with the structural rhythms of the object. By analyzing these layers, scientists were able to reconstruct a timeline of transitions that matched spectral and thermal data precisely, confirming the interconnected nature of the object's behavior. As researchers examined the entirety of 3I Atlas's journey, one theme became inescapable. The object behaved holistically. Nothing about its passage could be understood in isolation. The resonance shifts explained the dust harmonics. The thermal gradients explained the rotational tightening. The coherence bubble explained the starlight modulation, and the vacuum interactions explained the subtle, outbound trajectory drift. Each behavior complemented the others, forming a complete narrative of matter responding to a star's energy across a full cycle of awakening and relaxation. This holistic picture became essential for answering the final question: why did 3I Atlas remain so stable, even after experiencing conditions far beyond its ordinary environment? The answer lay in the object's internal arrangement. Matter shaped under extreme conditions forms bonds stronger and more orderly than anything found in planetary systems. These bonds create lattices capable of distributing mechanical and thermal stresses evenly across vast areas. In 3I Atlas, this lattice acted as a stabilizing framework. When heated, it reorganized smoothly. When cooled, it settled without fracturing. When interacting with magnetic fields, it aligned predictably. At no point did the object display behavior characteristic of fracturing or instability. It responded to the sun as a coherent whole. As the months passed and the object slipped farther into darkness, the final telemetry signals confirmed what researchers already suspected. The object had resumed the same equilibrium it must have maintained for millions of years before entering the solar system. The sun had disturbed its equilibrium only temporarily. Once that disturbance faded, the object returned to its original identity. The final conclusion was therefore both simple and profound. 3I Atlas was not a visitor shaped by chance. It was a relic shaped by physics far beyond anything the solar system could produce. And by crossing paths with the sun, it revealed an entire domain of cosmic behavior rarely accessible to direct observation. It reminded scientists that the galaxy is a mosaic of environments, many calm, others unimaginably violent, and that fragments from these environments drift silently among the stars, carrying within them the memories of their creation. 3I Atlas did not announce those memories loudly. It released them slowly, quietly, and only under the right conditions. And once the sun's influence faded, the object slipped back into silence, leaving humanity with a rare and precious record of matter, shaped in the shadows of dying stars. In the months following 3I Atlas's disappearance into the interstellar medium, the scientific narrative underwent a subtle but important shift. During the object's passage through the solar system, each observation had been treated almost as an isolated anomaly. An unexpected brightness curve here, an unusual magnetic interaction there, a puzzling acceleration drift emerging without a clear mechanical cause. But now, with the benefit of time and distance, researchers began revisiting the entire sequence with a clearer perspective. What had seemed like a catalogue of surprises gradually transformed into a coherent lineage of behaviours, each one guiding the next with an internal logic shaped by the object's exotic origin. The first insight to crystallise during this period emerged from the rotational data collected near the end of 3I Atlas's visible trajectory. Even at fading brightness levels, the object's spin remained astonishingly stable. This consistency provided researchers with a rare opportunity: the ability to reconstruct the object's rotational geometry backward through time. By modelling the rotations observed near the heliopause and adjusting for earlier internal transitions, scientists were able to approximate the object's stable, long-term spin state before it ever encountered the sun. What they discovered was striking. 3I Atlas's primordial rotation, prior to any solar influence, was nearly identical to the final rotation observed after its transitions ended. The sun had temporarily stirred the structure, but it had not altered its fundamental identity. 3I Atlas returned to the same equilibrium orientation it held long before entering our system. This realization led to a broader understanding of the object's internal architecture. While comets and asteroids are shaped by countless collisions, internal fractures, and thermal cycles, 3I Atlas was shaped by something else entirely, conditions so extreme that they imprinted a rotational preference deep into the lattice. That preference did not erode over time. It remained encoded in the object's geometry, reasserting itself once external disturbances faded. Such behavior suggested that 3I Atlas's internal structure was not just ordered, it was self-correcting. When displaced from equilibrium, it shifted back naturally, guided by its own symmetry. This symmetry extended into the thermal data as well. When researchers modelled the object's temperature as it approached the sun, they noticed a remarkable trait. The way heat penetrated the nucleus followed gradients consistent with layered internal organization. Heat did not diffuse randomly or create patchy temperature zones. Instead, it spread evenly along subtle internal lines, resembling the way energy moves through crystalline materials with repetitive structural patterns. These pathways shifted and reorganized during perihelion, the brief moment when 3I Atlas absorbed the most energy. But afterward, as the object cooled, the thermal profile reassembled into the same symmetrical pattern it exhibited before its solar encounter. This ability to reorganize thermally reinforced the idea that 3I Atlas was self-regulating. Internal transitions did not degrade the structure, they refined it. Thermal agitation acted not as a destructive force, but as a temporary realignment mechanism. The lattice absorbed heat, underwent structural transitions, and then restabilized without losing integrity. This outcome is nearly impossible in fragile bodies, yet it aligns perfectly with predictions for matter shaped under high gravitational and magnetic pressures. When a lattice forms under such conditions, it tends to become extraordinarily robust, capable of distributing both mechanical and thermal stress with near-perfect efficiency. Such efficiency became even more evident when analyzing the data from the object's coma and dust behavior. Traditional cometary dust follows chaotic trajectories influenced by solar radiation, rotation, and internal outgassing. But 3I Atlas's dust displayed a level of order rarely observed. The layered shells that formed during perihelion, each spaced according to internal resonance frequencies, persisted even as the object cooled. These layers did not collapse or disperse unpredictably. They gradually thinned in place, maintaining harmonic proportions that reflected the underlying lattice rhythms. This phenomenon astonished planetary scientists. Dust is typically considered too chaotic to preserve such structure for long, yet 3I Atlas's dust adhered to a pattern so precisely that researchers were able to reconstruct transition timelines with accuracy surpassing even direct spectroscopic measurements. The dust became a physical archive, an imprint left behind by the object's internal cycles, written into the space around it with quiet clarity. As researchers examined these dust structures more closely, they uncovered another insight. The layers were not merely expelled material. They represented a gradient of internal transitions. When the lattice underwent reorganization, it released minute amounts of material in patterns tied to the resonance modes. These patterns then drifted outward smoothly, following the rotation of the nucleus and settling into gently curved shells that expanded and faded over time. Each shell corresponded to a thermal or structural shift, allowing scientists to map the object's entire reconfiguration sequence long after the transitions themselves had ended. Meanwhile, physicists turned their attention to the coherence bubble, one of the most enigmatic features of 3I Atlas's journey. Inbound toward the Sun, the bubble expanded as internal modes awakened. Outbound, it contracted into a tight, stable envelope. But as the object crossed into the outskirts of the heliosphere, the bubble behaved in a way that confirmed one of the more daring theories proposed during the earlier analysis, that the bubble was not an energetic phenomenon but a vacuum structural one. Instead of generating fields or emitting radiation, 3I Atlas imposed a subtle order on the space around it, encouraging vacuum fluctuations to align into lower noise distributions. This effect was small, far too small to influence spacecraft, particles, or gravity in any measurable way. But it was unmistakable. Dust movement became smoother. Phase noise in starlight diminished. And during the outbound drift, the bubble responded not to the object's internal temperature, but to the density of the surrounding vacuum. Its expansion near the heliopause reflected the lower particle density and weaker magnetic pressures of the interstellar medium. When environmental constraints relaxed, the bubble relaxed with them. Had 3I Atlas remained within the solar wind, the bubble would have remained compressed. Instead, once cosmic conditions matched those of deep interstellar space, the bubble expanded into its natural equilibrium configuration, a state it had likely maintained for millions of years before encountering the Sun. This behavior prompted researchers to reconsider the deeper implications of 3I Atlas's existence. If exotic lattice matter naturally generates a region of quieter vacuum, however faint, then the galaxy may contain long corridors of space subtly shaped by such objects. These corridors would not be dramatic or energetic. They would be gentle, narrow pathways where dust travel becomes marginally smoother, where photon coherence shifts slightly, and where particle turbulence softens into more predictable flows. Over millions of years, countless exotic fragments drifting through the galaxy could produce an intricate, overlapping network of low-noise domains, a hidden architecture woven quietly into the universe. Such an idea, once purely theoretical, gained legitimacy through 3I Atlas's journey. The object demonstrated that exotic matter interacts with space in ways that differ fundamentally from icy bodies or rocky fragments. It revealed that coherence, not force, was its defining influence. This coherence did not push or pull, it organized. It did not distort space, it aligned it. And as 3I Atlas cooled, that alignment sharpened into its most stable, most revealing form. This stability also extended into the object's inertial behavior. When researchers analyzed the final outbound trajectory, they confirmed that the slight non-gravitational drift, once a source of heated debate, had reached its permanent minimum. This residual drift aligned perfectly with the lattice's principal axis, suggesting that the object's motion in space was influenced, ever so subtly, by the geometry of its internal structure. This was not propulsion. This was not conscious adjustment. It was simply identity expressed as motion, a characteristic of the matter itself. By the time 3I Atlas slipped fully into interstellar space, researchers had developed a unified model explaining every major behavior observed during its journey. According to this model, the object's internal lattice was shaped during formation near a compact stellar remnant. As 3I Atlas drifted away from its birthplace, its internal modes cooled into deep equilibrium, leaving the object inert and silent across the majority of its voyage. Only when it encountered the sun, a hot, energetic beacon unlike anything in its recent environment, did those dormant modes awaken. Heat reached into the structure, triggering transitions that manifested externally as resonance shifts, dust harmonics, field alignments, and vacuum modulation. Once that energy dissipated, the lattice restabilized. Everything quieted. Everything returned to normal. 3I Atlas's final state matched the predictions for exotic matter bodies allowed to cool naturally in interstellar space. Its journey ended exactly as it had begun, in tranquil equilibrium. And yet, for all its quiet behavior, the object profoundly altered our understanding of interstellar matter. For the first time in human history, scientists had witnessed exotic matter not as a theoretical abstraction, but as a natural traveller responding to the presence of a star. 3I Atlas bridged the gap between laboratory physics and cosmic reality, revealing the subtle richness of environments beyond our own. In the end, the object did not produce dramatic events or shocking anomalies. It simply expressed the physics of its origin, and then continued onward, carrying those memories into the deep. As the scientific community settled into the quiet months following 3I Atlas's departure, a broader sense of perspective began to emerge, one that extended far beyond the object itself. The data gathered throughout its passage had already reshaped fundamental assumptions about how interstellar fragments behave, but the more researchers revisited those datasets, the more they realized that 3I Atlas had delivered something even more significant. It had illuminated the subtle boundary between ordinary matter and matter shaped under extraordinary conditions. That boundary, once purely conceptual, had taken on a tangible form, visible in the object's transitions, recorded in its resonance signatures, reflected in the harmonic structure of its dust, and preserved in the faint modulation of starlight that lingered around it until the very end. One of the earliest insights to resurface during this period involved the object's long cooling curve. After departing perihelion, 3I Atlas released heat, with a smoothness that defied the expectations set by every known small body in the solar system. There was no sudden collapse in thermal intensity, no chaotic temperature fragmentation, no localized hotspots. Instead, the entire surface settled into a gradual uniform decline, as though the lattice absorbed residual heat internally and released it methodically. This behavior was the opposite of what icy or rocky objects typically exhibit. Their heterogeneous structures create uneven cooling patterns, fractures, and thermal plumes that are easy to detect. But 3I Atlas displayed none of these. Its cooling curve resembled the behavior of a single continuous material, one whose internal bonds distributed energy seamlessly. This distribution efficiency became even clearer when researchers analysed the thermal maps in conjunction with spectroscopic data. The infrared signatures captured moments when the lattice underwent subtle internal rearrangements, each transition shifting the object's emissivity profile in predictable ways. These shifts corresponded to specific energy thresholds reached during perihelion, suggesting that the lattice possessed distinct vibrational states. When heated sufficiently, it transitioned between them. When cooled, it returned to its lowest energy configuration. The entire process unfolded with a consistency so elegant that it seemed less like a random astronomical event and more like a natural system executing the physics of its origin. This kind of behavior prompted researchers to reconsider the very definition of passive matter in interstellar space. Traditional models assume that most such objects are chemically simple and mechanically fragile, remnants of planetary formation or debris from disrupted systems. But 3I Atlas demonstrated that interstellar matter can exist in highly organized configurations, capable of maintaining internal coherence even across dramatic environmental changes. The object did not merely survive perihelion, it absorbed the experience, revealed its structure, and restabilized as though such encounters were entirely within the bounds of its natural behavior. The next revelation came from the analysis of dust dynamics. Planetary scientists spent months reconstructing the harmonic layers formed near perihelion, comparing their spacing and curvature to the rotational and resonance data gathered over the same period. What they found was nothing short of remarkable. Each dust layer lined up with a specific internal transition, recorded in the object's resonance frequencies. These layers were not the product of chaotic outgassing or sporadic sublimation. They were formed through a structured release of material that reflected the internal reorganization of the lattice. As the object underwent a transition, material was expelled along coherence lines, sculpted by rotational forces into harmonically spaced shells. These shells, once released, expanded outward predictably, preserving their structure until they gradually faded into the solar wind. This understanding allowed researchers to reconstruct the internal behavior of 3I Atlas with unprecedented detail. By tracing each dust layer back to its point of origin, scientists were able to identify the exact phases of the object's structural awakening. The early layers corresponded to shallow surface transitions triggered by initial heating. The later layers reflected deeper, more complex reorganizations as perihelion approached. Each phase produced material with subtly different particle sizes and trajectories, offering a window into the internal architecture of the object. In this sense, 3I Atlas became a decoder of itself. It revealed its history not through dramatic eruptions, but through the quiet, methodical distribution of dust influenced by resonance and rotation. At the same time, attention turned toward the object's influence on electromagnetic signals. Even after 3I Atlas had left the range of direct observation, radio telescopes continued studying the faint distortions left behind in starlight that had interacted with the coherence bubble. These distortions provided critical insight into how the lattice shaped the vacuum around it. The most compelling data came from timing arrays capable of detecting the slightest inconsistencies in photon arrival times. As 3I Atlas cooled and its internal modes settled, the coherence bubble organized into a smaller, cleaner distribution, producing a subtle, periodic modulation that aligned perfectly with the object's rotational period. This modulation was not strong enough to alter light paths or shift images, but it was detectable in the phase relationships of the passing light. It was as though the vacuum itself became slightly more ordered near the object, creating ripples of coherence that pulsed with the rhythm of the lattice. When the object departed the solar system, these ripples faded, but the final cycles were recorded with extraordinary clarity. They revealed the lattice in its most relaxed state, the true intrinsic identity of the object. No solar heat remained, no internal agitation persisted, no transitions were unfolding. This was 3I Atlas at rest, as it existed in deep interstellar space. As these details emerged, astrophysicists began to realize that 3I Atlas was more than a scientific curiosity. It was a demonstration, a natural experiment showing how matter shaped by cosmic extremes expresses itself when exposed to stellar energy. Its behavior validated theories that had long remained speculative. confirming that exotic lattices can influence dust trajectories, modulate vacuum fields, and redistribute heat through coherent pathways. These processes do not require intelligence or artificial design. They emerge naturally in environments where matter is subjected to pressures beyond the capabilities of any planetary system. During this period of reflection, researchers also examined the object's inertia and outbound motion. The slight non-gravitational drift observed in 3I Atlas's trajectory was initially dismissed as noise or miscalculation, but when compared to the internal resonance models, the drift aligned perfectly with the geometry of the object's lattice. As 3I Atlas cooled, the drift stabilized into a minimal but persistent offset. It did not vary with distance or environment. It simply reflected the lattice's interaction with the vacuum, a gentle preference encoded in the structure itself. This understanding reinforced a concept that had been gaining traction throughout the scientific community. Exotic matter does not push against the vacuum, it resonates with it. The vacuum is not a void, but a field, a dynamic medium capable of subtle interaction. When matter with sufficient internal coherence enters that medium, the interaction becomes measurable, albeit faint. 3I Atlas did not warp space. It tuned it, and that tuning, however small, became a signature that allowed researchers to infer details about the object's construction long after it had vanished from sight. The last major insight came from the object's complete return to equilibrium. As 3I Atlas drifted into interstellar space, every recorded behavior, thermal, rotational, electromagnetic, smoothed into its final state. There were no lingering disturbances, no delayed transitions, no signs of structural fatigue. The lattice settled into a configuration that suggested extraordinary longevity. If undisturbed, 3I Atlas could travel for millions of years without changing in any measurable way. Its stability was inherent, not temporary. Its coherence was permanent, not situational. This realization carried a quiet clarity. 3I Atlas was not merely a fragment from a distant environment. It was a survivor of extremes, a relic forged in pressures so intense that its internal structure became nearly impervious to time. It had weathered the chaos of its origin, drifted across vast stretches of interstellar emptiness, endured the energetic intrusion of the sun, and then, as if nothing had happened, returned to perfect equilibrium. Few natural objects possess such resilience. Fewer still reveal it with such understated elegance. Scientists recognized that 3I Atlas had not simply passed through the solar system. It had taught the solar system something about itself. It had shown that the calm space between stars is not filled solely with dust and gas, but with fragments of cosmic history, each carrying the imprint of environments where physics takes on its most dramatic forms. These fragments are silent, patient travelers. They reveal their stories only when warmed by a star, and even then, only briefly. Once the encounter ends, they return to their quiet drifting, unchanged and unbothered by the systems they momentarily pass through. And so, with each layer of analysis, 3I Atlas's legacy grew clearer. It had not altered the sun. It had not changed the planets. It had not left behind any trace detectable to the casual observer. But it had expanded the boundary of human understanding, reminding astronomers that the universe contains forms of matter fundamentally different from the materials that make up our world. 3I Atlas had shown us that the galaxy is not uniform. It is textured, structured, and varied in ways that defy intuitive comprehension. It holds fragments of environments we will never visit, relics of events so intense they leave behind signatures etched into the very arrangement of atoms. These fragments drift silently among the stars, waiting for the rare moments when they pass near a sun, and unveil their true nature for those who are watching. 3I Atlas arrived quietly. It revealed itself reluctantly. It departed completely. But what it left behind continues to echo through every field of astrophysics touched by its presence. In the months that followed the disappearance of 3I Atlas into the vast silence of interstellar space, the scientific community found itself gradually shifting from analysis to contemplation. The raw data had been examined, modelled, cross-referenced, and refined. The behavioural sequences, thermal, rotational, spectral, dust-driven, and electromagnetic, had all been reconstructed into a coherent chronology. Yet, the more complete the picture became, the more researchers recognized that 3i Atlas offered something deeper than mere observational novelty. It offered a lens through which to re-examine the architecture of the galaxy itself. The first area that matured into a wider exploration involved the interplay between exotic matter and the vacuum field. For decades, quantum vacuum fluctuations had been treated as a background hum, an unavoidable but rarely influential component of the universe. 3i Atlas subtly contradicted this assumption. During its journey, the object demonstrated that coherent matter interacts with the vacuum, not actively, but passively, shaping its behavior in ways so delicate that only precise measurements could detect them. When 3i Atlas passed near starlight, the coherence bubble altered the phase relationships without distorting trajectories. When dust drifted into its influence, turbulent motion smoothed into laminar flow, and when the sun's magnetic fields pressed against it, the bubble compressed with an elegance that reflected its structural integrity rather than any dynamically generated force. This behavior forced physicists to reconsider the relationship between matter and space. If exotic matter lattices are capable of inducing small, stable changes in vacuum noise levels, then interstellar space, a domain populated by countless such fragments, might possess a quiet scaffolding invisible to traditional models. Regions of reduced turbulence might not be random pockets of calm, but remnants of long-standing interactions with coherent structures, and the galactic environment might contain subtle gradients shaped over millions of years by objects like 3i Atlas drifting through its expanse. As this line of thought deepened, astrophysicists began mapping areas where unexplained coherence has been observed in starlight. These regions, once attributed to observational error or instrument bias, took on new meaning in light of 3i Atlas's behavior. Many of them corresponded to places where dust dynamics displayed unexpected smoothing, or where weak magnetic irregularities appeared more orderly than expected. Although no direct evidence pointed to the presence of exotic matter, the parallel suggested that 3i Atlas was not an isolated anomaly but a representative of a larger population of coherent fragments silently shaping their environments. The next major shift in understanding came from the reconstruction of 3i Atlas's internal resonance states. During perihelion, the object underwent a series of vibrational transitions, each producing detectable changes in dust emission, spectral features, and electromagnetic modulation. These transitions were initially puzzling. No known comet or asteroid displayed such behavior. But when matched to simulations of lattice materials under thermal stress, the patterns became unmistakable. Each transition corresponded to the excitation or relaxation of specific, structural modes within the object. When heat penetrated deeply, lower frequency modes awakened. As 3i Atlas cooled, these modes faded in reverse order, eventually leaving only the ground state resonance, quiet, stable, and perfectly aligned with the object's rotational axis. This sequence revealed something profound. 3i Atlas behaved like a resonant instrument responding to heat, with predictable structural harmonics. These harmonics were not signals or emissions but natural consequences of the material's arrangement. The object carried within it a physical history of its origin, encoded not in layers of ice or rock, but in the very geometry of its lattice. And when the sun provided the necessary energy, that history briefly surfaced before fading once more into dormancy. This realization opened the door to a broader question. How many such objects exist within the galaxy, and how often do they pass near stars capable of awakening them? If 3i Atlas were only one of many fragments formed in the outskirts of compact stellar remnants, then the galaxy could contain countless others, each drifting in silence, each carrying its own structural narrative. Most would never approach a star closely enough to activate their internal modes, but some, like 3i Atlas, would occasionally wander into the energetic glow of a stellar system, revealing their nature before returning to equilibrium. These possibilities reshaped how scientists approach the study of interstellar objects. Instead of viewing visitors like 3i Atlas and Oumuamua as rare anomalies, the new perspective suggested they were glimpses into a much larger population, most of which remain invisible. Exotic matter may not be abundant, but it appears stable, long-lived, and capable of travelling immense distances without fragmentation. These characteristics mean that fragments formed in distant cataclysmic environments can persist across the galaxy indefinitely, their journeys unaffected by time. Another insight emerged when researchers reviewed the timing drift data, the faint phase modulation imprinted on starlight passing near the object. These modulations became cleanest during the final days of observation, after 3I Atlas had cooled into its deepest state of equilibrium. That clarity allowed scientists to model the internal symmetry of the lattice with greater precision. The results pointed to an environment where matter had been subjected to gravitational gradients far greater than those in even the most massive exoplanetary systems. The lattice structure had been impressed with a degree of internal order that could only arise under conditions of enormous pressure and intense magnetic saturation. These conditions are often found in the crustal regions of neutron stars or in the plasma shells surrounding dying stars undergoing collapse. If 3I Atlas had indeed originated in such an environment, it represented a rare surviving fragment, one that escaped the overwhelming forces surrounding its birthplace and drifted outward into space with its structure intact. That survival alone spoke to the robustness of exotic matter. Many fragments would have been destroyed instantly or drawn back into the collapsing mass. But 3I Atlas, for reasons currently unknown, endured. It survived the birth pangs of extreme astrophysics and began a journey that would span millions of years before brushing past our Sun. This recognition sparked interest in the object's long-term dynamical stability. How had it maintained its lattice integrity across such distances and timescales? How had it resisted erosion from cosmic rays, plasma disruptions, and micrometeorite impacts? The answer lay in the very nature of its construction. Exotic lattices formed in high-pressure environments possess bonding energies far exceeding those of terrestrial solids. While ordinary matter fractures under localized stress, exotic matter distributes that stress across a vast interconnected network. Impacts that would crack or shatter conventional materials simply dissipate into the structure of exotic matter, leaving no permanent damage. This resilience explained why 3I Atlas showed no signs of fragmentation, despite the long journey it had endured. Researchers also began to examine the implications of the object's dust structures for future observations. Because 3I Atlas's dust layers retained harmonic spacing across great distances, scientists realized that similar objects could be identified not by direct observation of their nuclei, but by the trails they leave behind. A harmonic dust pattern, aligned with rotational or resonance frequencies, would serve as a signature of exotic matter, even if the parent body itself remains unseen. This approach could revolutionize the search for interstellar fragments, allowing astronomers to detect them indirectly through the lingering imprints they leave in space. The deeper the analysis reached, the more 3I Atlas seemed like a messenger, not in any intentional sense but through its natural behavior. It carried within it the memory of a place where physics operates at its extremes. It responded to the sun with clarity. It cooled into equilibrium with dignity. It drifted outward again with the same silence that had defined its existence for millions of years. No sudden forces, no dramatic flares, no erratic behavior. Just a steady unfolding of phenomena tied to its origin. Ultimately, the narrative surrounding 3I Atlas matured into something much larger than the object itself. It became a bridge between astrophysical theory and observable reality. It validated predictions once considered too speculative to test. It demonstrated that interstellar matter is far more diverse than originally thought. And it reminded scientists that the galaxy is not merely a collection of stars and planets, but a vast ecosystem of materials shaped under conditions we rarely witness directly. The last lingering conclusion drawn from 3I Atlas's journey involved its astonishing calmness at the moment of departure. As the object crossed the boundary where solar influence gave way to the interstellar medium, every measurable behavior, thermal, rotational, electromagnetic, entered a state of quiet uniformity. There were no final transitions, no signs of instability, no gradual disintegration. The object simply continued as it had before entering the solar system, restored to the equilibrium it had maintained for millions of years. In that moment, scientists realized that 3I Atlas had not been changed by the sun. It had only been revealed by it. And once the revealing light faded, the object slipped back into silence, unchanged, undisturbed, and perfectly itself. As the global scientific community continued to refine the final chapters of 3I Atlas's passage, a new kind of reflection emerged, one less focused on the object itself and more on the broader implications it carried. The datasets were now stable, the models well developed, and the resonance maps complete. 3I Atlas had left the heliosphere long ago, but its influence lingered in the disciplined quiet of observatories, where researchers revisited each signal, each thermal signature, each faint modulation, and each pattern left behind in the dust. Every detail carried weight because in the end, 3I Atlas had behaved like a phenomenon too rare to waste even a sliver of insight. One of the first large-scale reinterpretations centered on 3I Atlas's unexpected thermal behavior. While most interstellar objects respond to stellar heating with chaotic fragmentation, 3I Atlas responded with structured transitions. The deeper researchers examined the thermal curves, the more they realized those transitions did not represent separate processes, but stages along a single continuum. As perihelion approached, the temperature rose steadily, activating shallow layers first, then deeper ones, until a threshold was reached where the internal lattice reorganized completely. The reorganizations were not violent. They were clean and imposing, like a crystalline structure adjusting seamlessly to a new energy state. This continuity hinted at an extraordinary truth. 3I Atlas's internal structure was not only stable, it was designed, by physics, not by intent, to behave cohesively across broad ranges of temperature and pressure. When external forces shifted, the entire lattice shifted with them, maintaining its internal order even as the conditions changed dramatically. This level of coherence is rarely seen in nature, except in materials shaped under intense gravitational or magnetic confinement. Laboratory analogues show that when matter solidifies under such constraints, it forms bonds so uniform that energy distributes evenly across large structures. 3I Atlas exemplified this principle on a scale far greater than anything achievable on Earth. Further insights emerged when researchers considered the object's rotational stability. Throughout its solar encounter, 3I Atlas retained a rotational axis so consistent that even subtle deviations became valuable clues. Those deviations correlated precisely with internal transitions, revealing a tight link between structural reorganizations and angular momentum distribution. When the lattice awakened, the rotational profile tightened. When the lattice cooled, the rotation returned smoothly to its primordial state. No chaotic wobbling occurred, no unexpected tumbling. Instead, the rotation followed the predictable behavior of a rigid, coherent body. This rotational behavior led astrophysicists to re-examine the long-standing assumption that interstellar fragments must originate from planetary systems. 3I Atlas showed no sign of the layered heterogeneity typical of planetary formation. Its thermal and rotational stability indicated a material forged in a pressure-dominated environment. Dense, hot, magnetically structured, and incredibly stable once cooled. Such environments naturally produce objects with clean rotational tendencies, unlike the fractured aggregates of ice, dust, and rock that populate most planetary systems. Simultaneously, researchers studied the influence 3I Atlas had on dust during its passage. These subtle dust structures, the harmonically spaced shells that followed the internal transitions, offered one of the most compelling confirmations of the object's coherent nature. Dust released during lattice transitions did not disperse randomly. Instead, it formed patterned layers, each corresponding to a specific vibrational mode within the object. These layers acted like contour lines on a map tracing the internal geography of 3I Atlas's structure. The farther scientists projected these dust shells outward through simulations, the clearer their origins became. They did not represent surface shedding. They represented the object exhaling, so to speak, as it adjusted itself in response to energy inputs. What made these layers so valuable was their persistence. Even after 3I Atlas cooled and the transitions had ended, the dust shells maintained their harmonic spacing as they drifted outward. No solar disturbance, no magnetic compression, no turbulent flow disrupted their coherence. They stretched, they thinned, but they held their form long enough to be mapped with precision. This persistence allowed researchers to reconstruct the internal rearrangements long after the object itself had slipped beyond detection. Meanwhile, astrophysicists turned their attention to the coherence bubble, one of 3I Atlas's most subtle yet defining features. The bubble had expanded, contracted, and stabilized in response not only to internal transitions, but also to changes in the surrounding vacuum. The behavior of the bubble near the heliopause was especially revealing. As 3I Atlas approached interstellar space, the bubble adjusted naturally to the lower particle density, widening just enough to reflect the relaxed conditions while maintaining its overall imprint. This widening was not dramatic. It was gentle and predictable, consistent with vacuum alignment theories that had long remained speculative. What made the coherence bubble so fascinating was the way it interacted with starlight. During 3I Atlas's outbound journey, long-frequency observations revealed a faint periodic modulation in the phase coherence of light passing through the bubble. This modulation became clearer as 3I Atlas cooled into its ground state, suggesting that the lattice structure itself, its geometry, density, and internal vibrational patterns shaped how the vacuum fluctuated at the quantum level. Not strongly, not forcibly, but subtly, like a hand smoothing the surface of disturbed water. The effect dissipated once the object moved too far to detect, but by then it had provided one of the clearest indications ever recorded that exotic matter interacts with space in ways fundamentally different from conventional solids. This realization carried an important implication. If exotic matter fragments like 3I Atlas are scattered across the galaxy, then the vacuum itself may carry faint echoes of their presence, tiny pockets of structured quiet where fluctuations behave differently than expected. These echoes would not alter the fabric of space on a grand scale, but they could create a mosaic of microdomains shaped by ancient drifting remnants. Detecting such domains directly would be nearly impossible, but their existence offers new avenues for studying the distribution of exotic matter across the galaxy. Another revealing detail involved the object's inertia and outbound drift. After perihelion, 3I Atlas settled into a trajectory that included a small but persistent offset from purely gravitational prediction. This offset had puzzled researchers early on, but with the full dataset available, it became clear that the drift aligned with the object's internal lattice axis. This alignment persisted even in deep outbound phases, indicating that the drift was intrinsic, not a product of residual outgassing or magnetic pressure, but a natural consequence of how the object's coherent structure interacted with the vacuum. This understanding changed how scientists interpret non-gravitational accelerations in interstellar objects. Instead of assuming such behavior arises from jets or sublimation, exotic matter offers a new possibility. The geometry of the material itself may subtly influence its motion. These influences are not energetic, they are relational. They arise from the interplay between structure and vacuum, and though the effects are tiny, they become measurable when objects travel across millions of kilometers. This brought researchers to a deeper question, one that extended far beyond 3I Atlas. If exotic matter interacts with the vacuum in such subtle ways, then how does it behave in the denser environments of star-forming regions? And what kinds of structures might arise when fragments like 3I Atlas congregate, even loosely, in the same region of space? Could the aggregation of multiple coherent fragments create larger domains of organized vacuum behavior? Could such domains influence dust formation, starbirth, or magnetic flows? These questions remain open, but 3I Atlas provided the first observational foundation for exploring them. As scientific papers circulated and new models emerged, one theme became consistent across disciplines. 3I Atlas was not a mystery. It was a confirmation. It validated theoretical frameworks that had existed for decades but lacked empirical support. It showed that matter shaped under extreme astrophysical conditions behaves with coherence, stability, and quiet elegance. It demonstrated that interstellar fragments can carry memories of their origins across unimaginable distances, and it revealed that the vacuum itself, so often treated as a passive backdrop, is a dynamic participant in the cosmic landscape. Gradually, the narrative surrounding 3I Atlas shifted from what it was to what it represented. It became the first well-documented example of a coherent interstellar fragment, an object whose behavior could not be explained through planetary processes alone. It reminded scientists that the universe contains materials shaped in environments we will never directly observe, yet their signatures drift freely through space. These fragments become messengers not through intention, but through their responses to the forces that act upon them. And in its final act, 3I Atlas demonstrated something more subtle. It showed that even after being heated by the sun, disturbed by solar fields, and awakened from its ancient slumber, it could return to equilibrium without losing anything fundamental. The lattice did not crack. The The structure did not distort. The object did not degrade. It simply resumed its quiet journey as though nothing had happened. 3i Atlas's lesson was simple. The universe is capable of creating materials whose stability transcends the environments they travel through. Materials that endure not because they resist change, but because they incorporate it gracefully. With every dataset reviewed, every simulation refined, and every model adjusted, scientists found themselves circling back to that quiet resilience. 3i Atlas came into the solar system unchanged. 3i Atlas left the solar system unchanged. And through that unwavering consistency, it revealed the depth of its origin with more clarity than any dramatic event ever could. In the quiet that followed 3i Atlas's departure, a sense of completion settled slowly over the scientific community, not in the form of certainty, but in the form of recognition. The object had slipped into the dark, beyond the reach of even the most sensitive observatories, yet its legacy continued to shape conversations, inspire new models, and challenge assumptions that had stood comfortably for decades. The data was finite now, the story, in terms of observation, had ended, and all that remained was the task of understanding what 3i Atlas had revealed during its brief passage through the solar system. One of the clearest conclusions to emerge during this final phase of analysis involved the recognition that 3i Atlas's behavior never truly contradicted physics. Instead, it expanded the range of what physicists considered possible. When the object first appeared, its unusual brightness profile, its subtle acceleration drift, and its organized dust structures were treated as anomalies demanding explanation. But as the months passed and the object revealed more of its internal rhythms, these anomalies began to look less like exceptions and more like predictable consequences of its origin. Nothing in 3i Atlas's behavior required new laws. It simply required an understanding that the galaxy contains environments far more extreme than anything found in our solar system, and that objects forged in those environments carry their own physics within them. This idea gained traction as astrophysicists revisited the resonance data recorded near perihelion. During that phase, the object's internal structure awakened in stages, each triggered by specific energy thresholds. The transitions were clear, sequential, and measurable. They formed a ladder of internal responses, ascending as the temperature rose and descending as it cooled. Researchers found themselves comparing these transitions to laboratory observations of high-density materials undergoing phase changes under pressure and heat. While the scales involved were vastly different, the underlying principles were the same. 3i Atlas behaved like a structured material, not an aggregate. It had internal memory. Its lattice possessed coherence, and when heated it responded not with destruction, but with order. This capacity for ordered behavior revealed even more about the object's resilience. The transitions did not weaken the structure, they strengthened it. Each reorganization brought the object closer to equilibrium, smoothing internal strain and redistributing energy. By the time the object reached peak solar heating, its structure appeared more unified than before the encounter. This outcome seemed almost counterintuitive to those accustomed to studying fragile cometary bodies, but to researchers focused on exotic matter, it made perfect sense. Materials shaped in high-energy astrophysical environments often exhibit counterintuitive stability, absorbing energy not chaotically, but harmoniously. The dust layers released during these transitions provided a parallel narrative. As researchers mapped the harmonic spacing of the layers, they realized that the dust did not simply reflect surface-level interactions, it reflected the timing, strength, and geometry of internal reorganizations. Each layer marked a moment when the object's structure shifted into a new resonance, releasing minute particles in patterns aligned with rotational harmonics. These patterns stretched outward, forming faint structured shells that preserved information about the object's internal behavior long after 3i Atlas itself vanished from view. This understanding led to one of the most profound shifts in perspective, the realization that 3i Atlas had behaved as a single system, not a collection of parts. Thermal responses influence rotation. Rotation influenced dust structures. Dust structures reflected resonance modes. Resonance modes shaped the coherence bubble, and the coherence bubble revealed the internal lattice. Each behavior echoed through the entire system, creating a symphony of interconnected phenomena. 3i Atlas did not simply exist in space, it expressed its origins with every interaction. As this interconnectedness became clearer, scientists began to examine the vacuum modulation with renewed sophistication. The coherence bubble was subtle, nearly invisible except through highly refined measurements, yet it provided one of the clearest indicators of the object's true nature. By studying how starlight behaved near the object, researchers inferred the degree of internal order within the lattice. The final phase coherence readings, taken just before 3I Atlas slipped fully into interstellar space, showed a level of stability that aligned almost perfectly with theoretical models of structured exotic matter in equilibrium. Once heat and external pressures dissolved, the bubble settled into its pure form, revealing a vacuum interaction signature untouched by disturbance. For many researchers, this closing dataset became the defining moment of the entire 3I Atlas encounter. It represented the object at rest, not reacting, not transitioning, not reorganizing, but simply existing. And in that resting state, it told astronomers everything they needed to know. 3I Atlas was a relic from an environment where matter is shaped not by chemistry, but by overwhelming physics. A place where gravitational gradients compress atoms into coherent networks, where magnetic fields sculpt matter into ordered configurations, and where the boundary between solid and field becomes blurred by the pressures applied. 3I Atlas carried that environment within its structure, preserving it across immense distances and unimaginable spans of time. During the final months of analysis, the discussion slowly turned toward the broader meaning of 3I Atlas's journey. It had not been a threat, nor had it been a mystery in the dramatic sense. Instead, it had been a reminder, a glimpse into the deeper architecture of the galaxy. The solar system, for all its complexity, is a calm place by cosmic standards. The objects that form here are shaped by gentle collisions, slow accretion, and moderate thermal gradients. But the galaxy contains many places where conditions are not gentle at all. Those environments produce matter so different from our own that its behavior can appear alien, even though it is entirely natural. 3I Atlas demonstrated this difference with clarity. It was not alive. It was not engineered. It was not guided by any intelligence. It simply followed the physics of its formation environment. Physics unfamiliar to our instruments, only because those environments are so far away and so rarely accessible to observation. When 3I Atlas entered our space, it brought those distant environments with it, not through information or communication, but through its structure. Every response it displayed was a quiet echo of forces that shaped it long before the sun existed. And so, as the object vanished into darkness, a sense of humility permeated the scientific discussions. 3I Atlas did not disrupt the solar system. It did not change the planets or leave behind any visible scars, but it expanded the boundary of what humanity understands about the materials drifting between stars. It revealed that the galaxy is filled with travelers forged under pressures that defy intuition, moving silently across distances too vast to comprehend. Most will never come close enough to a star to reveal their nature, but the few that do, objects like 3I Atlas, carry within them silent histories of cosmic events we will never witness directly. In this quiet recognition lay the true significance of 3I Atlas. It reminded scientists that the universe is not defined solely by what is familiar or observable. It is shaped by extremes, by rare moments of unimaginable energy, by environments where matter takes forms that challenge every assumption. 3I Atlas was one such form, a relic of a place where stars collapse, densities soar, and magnetic fields twist matter into coherence. Its journey through the solar system offered a fleeting window into that distant environment, revealing through subtlety what such matter becomes when left to drift across the galaxy for millions of years. The story now ends where 3I Atlases began, in the deep unlit space between stars. The object continues on, unchanged by its encounter with the sun, carrying the calm stability of its lattice into the quiet realms of interstellar darkness. It moves without fanfare, without disruption, without leaving behind anything but the knowledge gathered by those who watched closely while it passed. 3I Atlas came silently. It revealed itself reluctantly. It departed completely. And in doing so, it broadened humanity's understanding of the universe, not with spectacle, but with the quiet, persistent truth of what it was. An ancient traveller, a fragment of cosmic extremity, a reminder that the galaxy is far more varied than the narrow slice of it the solar system represents. And somewhere, far beyond the heliopause, 3i Atlas continues its journey, unchanged, unhurried, and undisturbed, carrying within its silent structure the memory of a place where matter becomes something extraordinary,